How do factories push mountains of onions, garlic, and bell peppers through steel machines without turning them into mush? One harsh drop, one missed mold spot, or one wrong temperature can ruin tons of produce in a single shift. In this video, we follow the process from harvest bins to cold chain packing, revealing the critical checkpoints that keep every bulb and pepper shelf ready. Raw onions become a consistent retail product inside a packing facility by being dried and stabilized, cleaned, graded by size and quality, trimmed, cured if needed, then packed under airflow conditions that preserve firmness and limit sprouting. The process starts with bulk bins, entering a receiving line designed for a crop that bruises less than fruit but still damages easily at neck and scale layers. Bins are tipped onto a receiving conveyor with controlled drop height. The infeed spreads onions into a single moving layer, so downstream cleaning is uniform. Conveyors use flights and side guides to prevent rolling pileups that can crack outer skins. Field material is removed early. The onions pass through a scalper where loose soil, stones, and plant fragments fall through screens. A parallel air separation stage lifts light chaff and dry tops away from the heavier bulbs. This early separation protects later brushing and sizing equipment from abrasion and reduces dust load inside the plant. Curing or conditioning is a central step for raw onions because outer skins and neck tissue must be dry before long storage and retail packing. If onions arrive partially cured, they still often enter a forced air curing tunnel. In a curing tunnel, onions sit in bins or flow through a bed while warm, dry air moves through them. Air temperature is controlled so it dries skins without cooking the bulb. Air humidity is controlled so drying continues efficiently. Airflow is designed to move through the pile rather than around it because onion drying is limited by how fast moisture leaves the neck and outer scales. Curing targets a dry neck and a tight, papery outer skin. A dry neck reduces rot risk and reduces sprouting. A tight skin protects the bulb during later handling and provides the familiar dry onion appearance. Curing duration depends on incoming moisture and bulb size, but the technical goal is consistent moisture at the outer layers, so later brushing does not peel too deeply. After curing, the onions move into cleaning. Cleaning focuses on removing loose skins and soil while keeping enough skin to protect the bulb. Rotary brushes scrub the surface and loosen brittle outer layers. Brush stiffness and speed are tuned so skins shed without gouging. A counter-rotating brush bank can be used to lift skins at multiple angles. Dust extraction hoods remove the shed skins and dry dust. Dust removal is important because airborne skins can clog screens and contaminate weighing systems. Roots and tops are handled next, depending on how the onions arrived. Some onions enter with tops already removed. Others enter with dried tops still attached. A topper cuts the neck to a specified length. Cut length is controlled because too long creates tangles in bagging and too short exposes moist neck tissue. A root trimmer removes roots flush with the basal plate without cutting into the plate. Cutting into the basal plate increases decay risk. Trimming systems use rotating blades or abrasion heads with guides that center the bulb. After trimming the onions, pass through a second cleaning stage. This stage removes fragments created by topping and root trimming. A combination of brushes and air knives lifts loose skins. Screens remove small fragments and soil. The line aims to deliver a clean bulb with intact protective skins. Sizing and grading follow. Onions are graded primarily by diameter and by external quality. Diameter sizing is done with roller sizers, belt sizers, or optical measurement systems. In roller sizing, the gap between rollers increases along the machine. Smaller onions fall through earlier gaps and larger onions ride further. This creates size classes for different retail packs. Optical sizing uses cameras to measure diameter as onions roll. The measured size triggers diverters that route onions to dedicated lanes. Quality grading is added to remove defects that would fail retail standards. Optical systems can detect bruises, cuts, mold, rot, and excessive skin loss. They can also detect green necks and splits. Split bulbs are a defect because they break down quickly and do not pack well. Sorting can be done with air jets or gates that remove defective bulbs from the flow. For defects that are hard to see externally, some lines use density-based methods or near-infrared sensing to estimate internal issues, but the main control remains external defect removal and dry neck verification. After grading onions, often enter a polishing step. Polishing uses softer brushes to smooth the outer skin and improve appearance. The goal is not shine like waxed fruit, but uniform skin and removal of remaining loose flakes. Polishing also reduces the amount of loose skin that ends up in bags. At this point, the line splits into multiple packing formats. One route is loose bulk cartons for food service and wholesale. Another route is consumer bags in specific weights. Another route is small tray packs or mesh sleeves. For bulk cartons, onions feed into a carton filler that drops bulbs in layers. Drop height is controlled to prevent bruising at the basal plate. Cartons are sized to the onion class. A pad can be used to reduce abrasion during transport. Cartons are closed and taped. Codes are printed for traceability. Weight checks confirm cartons meet target gross weight. For consumer bags, onions are portioned by weight. A weigher accumulates onions until target weight is reached. The portion drops into a bag former. Bags can be mesh for airflow or film with perforations. Mesh is common because onions need ventilation. Bagging equipment forms and seals the bag. Seal timing is set so no onion sits in the seal zone. A tag or label is applied. Bags are then collated into cases or onto trays. For small net sleeves, the line uses a sleeve applicator that stretches a tubular net over a set of onions. A clip seals both ends. This format demands tight size control, so the sleeve tension stays consistent and does not crush bulbs. Throughout packing, ventilation is treated as a product requirement. Onions release moisture and gases during storage. Packages therefore include ventilation holes or mesh to reduce condensation. Cases are designed with vents aligned to allow airflow through stacks. This airflow helps keep bulbs dry and slows sprout development. Storage and staging are integrated into the packing workflow. Packed onions may be held in cool, dry rooms before shipping. Temperature is held low enough to slow sprouting, but not so low that skins become brittle and crack during handling. Humidity is controlled because high humidity softens skins and encourages decay. Low humidity dries skins further but can increase skin flaking. Airflow is used to keep conditions uniform through stacked pallets. If onions are destined for longer storage before packing, the facility uses bulk storage bins with forced air ventilation. Onions are loaded into large bins and air is pushed through to remove residual moisture and to maintain temperature. Sprout suppression can be part of the broader supply chain strategy, but the mechanical packing process relies primarily on curing, temperature control, and ventilation. A separate route exists for peeled raw onions used in food service. In this route, onions are graded and then sent to peeling equipment. Peeling begins with scoring the outer skin and then using air blasts to lift skins away. A mechanical peeler can roll the onion against abrasive surfaces to remove outer layers. The peeled onions are then washed to remove skin fragments and drained. Trimming removes remaining root plate fragments and neck tissue. Peeled onions are then sized and packed in bags with controlled drainage. This route requires tight sanitation control and cold handling, but the core mechanical steps are scoring, peeling, washing, trimming, and draining. Garlic becomes a consistent retail product inside a packing facility by being cured to stabilize skins and cloves, cleaned, trimmed, graded by size and quality, then packed in ventilated formats that preserve dryness and limit sprouting. The process begins when bulk bins or totes of garlic enter the receiving line. The first objective is to move the bulbs from field containers into a controlled flow without tearing skins or snapping necks. Hydraulic bin tippers discharge garlic onto cushioned conveyors with low drop heights. Side guides spread bulbs into a single layer, so cleaning and grading equipment sees each bulb rather than a pile. Conveyor speeds are set to avoid rollback that cracks outer wrappers. Field debris is removed early because dry leaves and soil create dust that interferes with sizing and increases abrasion. Garlic passes over scalping screens where loose soil and small stones drop through. An air separation stage lifts light dried tops and chaff away from the heavier bulbs. Dust extraction hoods capture fine particles so they do not circulate and settle on sensors and belts. Curing is a central garlic-specific step because long storage performance depends on drying the neck and tightening outer skins. If garlic arrives partially cured, it still typically enters forced air curing tunnels or bulk curing rooms. Bulbs are loaded into ventilated bins or spread in shallow beds. Warm, dry air is pushed through the mass. Air temperature is controlled so moisture leaves quickly without softening cloves. Air humidity is controlled so drying potential stays high. Airflow is directed through the pile rather than over it because neck drying is limited by how fast air can. Remove moisture at the bulb surface. Curing targets several physical outcomes. Outer wrappers become papery and resistant to abrasion. The neck dries and seals, so microbes and moisture cannot travel into the bulb. Cloves stabilize and become firm rather than watery. Curing time is tuned based on bulb size and initial moisture. The facility monitors outlet air humidity and bulb wrapper feel as process indicators. The objective is a stable dry bulb that can be brushed and trimmed without tearing deep layers. After curing, garlic enters cleaning, where the goal is to remove loose skins and soil while keeping enough wrapper layers to protect the cloves. Brush beds rotate the bulbs and sweep away brittle outer skins. Brush stiffness is chosen to avoid scuffing that exposes cloves. Brush speed is tuned so bulbs roll and contact brushes evenly rather than sliding. Air knives and aspiration remove loosened skins from the stream. Skin removal is controlled because excessive removal reduces shelf protection and increases dehydration in retail packs. Trimming prepares the bulb for consistent presentation and prevents tangles in bagging. Top trimming cuts the dried stem to a specified length. Cut length is controlled because too long catches in mesh packs and too short can expose the neck opening. Root trimming removes root remnants flush to the basal plate without cutting into the plate. Cutting into the basal plate can open pathways into cloves and reduce storage stability. Trimmers use rotating blades or abrasion heads with guides that center the bulb so the cut is consistent. After trimming, the bulbs pass through a second cleaning stage to remove fragments created by cutting. Gentle brushes smooth the wrapper and remove remaining loose flakes. Aspiration captures debris so it does not enter weighing systems. The cleaned bulbs then move into sizing and grading. Sizing is usually based on bulb diameter. Roller sizes, belt sizes, or optical systems classify bulbs into size bands. Roller sizes use parallel rollers with widening gaps. Smaller bulbs drop through earlier and larger bulbs ride further. Belt sizes use diverging belts that create increasing openings. Optical sizing uses cameras to measure diameter as bulbs rotate on rollers. The measurement system assigns each bulb to a lane that corresponds to a pack size class. Quality grading removes bulbs that would fail appearance or storage targets. Optical inspection systems evaluate surface color uniformity, wrapper integrity, and visible defects. They detect split bulbs, exposed cloves, mold, soft spots, and excessive scuffing. Split bulbs are a major defect because they dehydrate fast and do not hold shape in packs. Bulbs with missing wrapper layers are also flagged because cloves can show and lose moisture. Sorting uses air jets or gates to divert defects out of the main stream. A separate grading decision can be made for bulbs with attached stems when braided products are produced. In that case, the facility routes long stem garlic to braiding lines and short stem garlic to standard pack lines. Braiding requires stems that are dry, yet flexible enough to be woven. Stem moisture and flexibility are therefore controlled during curing. Braiding lines separate bulbs by stem length and wrapper strength. After grading some lines, use a polishing step that improves appearance. Polishing uses softer brushes to smooth wrapper layers and reduce loose skin flakes. The purpose is not shine, but uniform wrapper texture. Polishing also reduces dust inside consumer packs. Packing formats for garlic are chosen to support ventilation and prevent condensation. The most common formats are mesh bags, net sleeves, and small cartons with ventilation holes. Garlic must breathe because residual moisture and respiration gases can accumulate in sealed packs and lead to mold. The packing line, therefore, uses materials with airflow paths. For mesh bags, garlic is portioned by weight. A scale accumulates bulbs until the target weight is reached. The portion drops into a bag, former that opens a mesh bag. The bag is sealed with a clip or heat seal depending on the material. Seal timing is set so no bulb sits in the seal zone. A label tag is applied. The filled bags are then conveyed to case packing. For net sleeves, the line forms a tubular net and loads a fixed count or weight. Clips seal the ends. Sleeve tension must be controlled because excessive tension can crush wrappers and create bruising at the basal plate. Size consistency is important in sleeves because larger bulbs increase tension and can distort the pack. For cartons or trays, bulbs are arranged in a single layer or in small stacks. Inserts can prevent rolling. Cartons are closed and taped or glued. Vent holes are lined to allow airflow through stacked cartons. Coding prints size class and lot identity. Check weighers verify carton weight within tolerance. For braided garlic, the process adds a weaving stage. Selected long stem bulbs are aligned and then woven into braids using guided fixtures. The braids are tied and trimmed. Braids are then packed in cartons with supports that prevent crushing. The braiding process relies on stems being dry enough not to mold, yet flexible enough not to snap. That balance is achieved during curing and by controlling humidity in the braiding room. Some facilities also produce peeled garlic and garlic cloves for food service. This route starts with graded bulbs that are sent to a breaking system. Breaking separates bulbs into individual cloves by mechanical cracking and rubbing. The cloves pass through an air separation system that removes papery skins. Additional peeling can use abrasion or air blast to lift remaining skins. Peeled cloves are washed briefly to remove skin fragments and then drained. Drain control is important because free water reduces shelf stability. The cloves are then sized and packed in sealed bags with controlled gas permeability, and then chilled quickly. Storage and staging are integrated into garlic packing because temperature and humidity control determine sprouting and mold risk. Packed garlic is held in cool, dry rooms. Temperature is kept low enough to slow sprout development. Humidity is kept low enough to prevent wrapper softening, but not so low that wrappers become overly brittle and flake. Airflow is managed, so conditions are uniform through pallets. Ventilation in cases and pallets allows air to move through stacks. Bell peppers become a consistent retail product inside a packing facility. by being unloaded with low impact, washed and dried, sorted by size, color, and defect, then packed in protective formats that prevent scuffing and dehydration. The process begins at receiving, where bulk bins or field totes are introduced to a line designed for delicate skins. Peppers are tipped by hydraulic dumpers onto cushioned conveyors with very low drop height. The goal is to avoid compression bruises and skin tears that later become soft spots. In-feed belts spread peppers into a single layer so they do not rub against each other in piles. Side guides and belt speeds are tuned to prevent rollback and pinch points. A dry debris removal stage often comes first. Air knives blow off loose leaves and dust that would otherwise contaminate wash water. A scalping screen can remove stones and hard debris that could gouge skins downstream. Once gross debris is reduced, the peppers enter washing. Washing starts with a pre-rinse that removes surface soil and field dust. Spray bars deliver water at controlled pressure so the skin is cleaned without forcing water into the stem cavity. Water is filtered continuously because suspended grit can scratch the glossy surface. After pre-rinse peppers pass through brush washers where soft rotating brushes scrub the surface. Brush stiffness is chosen to avoid dulling the skin. Brush speed is set so peppers rotate and contact brushes evenly, rather than sliding. After brushing a clean rinse, stage flushes away loosened residues. Drain belts remove free water. Drying follows because wet peppers scuff easily and water droplets interfere with optical sorting. Air knives remove surface droplets, and a drying tunnel uses moving air to bring the surface to a consistent dry state. Air temperature is kept moderate so the fruit does not warm and soften. The drying goal is a dry skin with minimal water trapped near the stem. Sorting and grading begin once peppers are clean and dry. Singulation is the first step in grading because sensors require isolated items. Singulation belts separate peppers with controlled spacing. Rollers can rotate peppers so cameras see multiple views. Spacing is maintained so diverters can fire accurately. Optical inspection systems capture images under controlled lighting. Lighting is designed to reveal color uniformity and surface defects. Cameras measure size, shape, and color stage. They detect scuffs, cuts, sunken bruises, blossom end issues, and skin cracking. The system can also flag soft rot indicators when discoloration patterns match known defect signatures. Each pepper is assigned a grade and a destination lane. Color sorting is important because peppers can be green, red, yellow, or orange, and color uniformity is a retail requirement. Optical systems quantify hue and saturation. Mixed color peppers or uneven color peppers can be routed to processing grades. Uniform colored peppers are routed to premium packs. Sorting can also separate by gloss and by skin texture because dull peppers often indicate dehydration. Size grading is performed alongside quality grading. Size can be estimated from image geometry or measured by mechanical sizing cups. Many systems use weight grading as well because pepper density varies. Weight is recorded by in-motion scales that support the pepper briefly. Size and weight together support pack count targets and uniform appearance in trays. After the inspection zone, the line uses diverters to route peppers. Diverters are timed gates or air jets that move peppers into different lanes. Impact control at these diversion points is critical. Chutes are lined and curved. Drop heights are minimized. Accumulators buffer flow so peppers do not jam and compress. Each lane feeds a specific packing format. Some lines include stem trimming or calyx cleaning. Trimming is minimal because peppers are sold with stems, but excessive stem length can puncture adjacent peppers in packs. If trimming is used, it clips stems to a controlled length without damaging the calyx. Calyx damage increases moisture loss and rot risk. The trimmed peppers then pass through a brief air dry stage to remove any moisture at the cut site. Waxing is not always used for peppers, but a light surface treatment can be applied to reduce dehydration in longer distribution. If applied, it is done as a fine mist while peppers rotate. The coating is very thin because heavy films can trap moisture and dull the natural gloss. After application, peppers pass through a short drying tunnel to set the film. Packing is designed to protect skins from abrasion. The most common premium format is tray packing. Trays have cavities that hold each pepper and prevent rolling. Tray selection matches pepper size class. Trays are fed by a denister and placed on a conveyor. Peppers are placed into trays by synchronized drop lanes or robotic pick systems. Placement is oriented so stems do not face outward toward film surfaces or neighboring peppers. After trays are filled, they are overwrapped or lidded. Overwrap film is stretched over the tray and sealed. Film tension is controlled so it holds peppers without crushing them. Vent holes can be included to prevent condensation. Lid seal systems use heat sealable films with controlled dwell time. Clean seals matter because leaks change humidity inside the pack and accelerate dehydration. For value packs, peppers can be packed in bags, often as mixed color packs. Bagging begins with portioning by count or by weight. Counting systems use gates and sensors to assemble a defined number. Weight systems use scales to hit target mass. The portion drops into a bag former. Bags are sealed and labeled. Bag material selection balances ventilation and moisture retention. Too much ventilation accelerates dehydration. Too little ventilation can trap moisture and promote soft spots. For bulk cartons, peppers are packed in layers with pads or liners. Liners reduce scuffing and help manage moisture. Carton fill is done with controlled drop heights and layer formation so lower peppers are not crushed. Cartons are closed and taped or glued. Vent patterns in cartons support airflow in cold storage. Cooling and cold chain management are integrated into pepper packing. Peppers are sensitive to heat and soften quickly if held warm. Many facilities pre-cool peppers before packing or immediately after packing. Forced air cooling is common. Packed cartons are stacked with vent alignment and fans pull cold air through the stack. Cooling rate is controlled to reduce water loss. Humidity in cooling rooms is maintained to prevent excessive dehydration while still avoiding condensation. Temperature targets are chosen to slow respiration and preserve firmness. Stable temperature prevents sweat formation on skins. Sweat leads to slip and scuff and later soft spots. The packing line therefore tries to keep peppers near a stable temperature from wash through pack, and it avoids warm air pockets around dryers by using moderate air temperatures. If the facility also produces cut peppers, the process branches after grading. Selected peppers enter a cutting room where they are washed again and then cored and sliced. Core removal cuts away the seed cluster and white ribs. Slicing blades are sharpened to avoid tearing skins. Slices are washed lightly to remove seeds and then dried by centrifuge or air. The slices are portioned and sealed in bags or trays and then chilled quickly. This route relies on very tight temperature control because cut peppers dehydrate fast. Quality checks occur throughout. Visual checks confirm color uniformity and defect rates. Weight checks confirm pack targets. Seal checks confirm package integrity. Rejected peppers are routed to processing grades or removed. The goal is to maintain grade purity and reduce damage introduced by the line itself. It all starts with malted barley, the soul of the beer. In a factory setting, the malt arrives by truckloads or freight trains already malted at a dedicated malting facility. Malting is a process in itself. Barley is soaked, allowed to germinate just enough to activate enzymes, and then dried and kilned to stop the growth. This controlled germination unlocks starches and enzymes that will later convert to fermentable sugars. The exact roast of the malt, pale, caramel, a chocolate, black, determines much of the final beer's color and flavor. For large-scale beers, base malts are used, usually lightly kilned, with small amounts of specialty malts blended in. The malt is piped into massive silos at the brewery, where it's stored dry and clean. When brewing begins, the malt is sent through a series of conveyors or airlifts to the mill. Here, roller mills crush the grain, not into flour, but into coarse grist. The idea is to crack the husk while leaving the interior accessible. Too fine, and the mash will become sticky and hard to filter. Too coarse, and sugar extraction drops. The grist is collected and weighed, then transported directly to the mash tun where the real transformation begins. In the mash tun, often a stainless steel vat the size of a swimming pool, the grist is mixed with hot water to form a thick porridge-like slurry. This step, called mashing, activates enzymes like amylase, which convert starches into simple sugars. The temperature is held precisely, usually around 65 and 68 degrees Celsius, depending on the style of beer. Too hot and the enzymes are denatured. Too cold and the starches won't fully convert. The mash is gently stirred using mechanical arms to ensure uniformity. For the next hour or so, the grain slowly transforms into a sweet liquid known as wort. When conversion is complete, the mash is transferred to the lautering vessel, sometimes built into the same tank. Lautering is the process of separating the liquid wort from the spent grain. A false bottom or fine slotted plates allow the liquid to drain through, while the grain bed itself acts as a natural filter. More hot water, known as sparge water, is sprayed over the top to rinse out every last bit of sugar. The collected wort flows to the brew kettle, while the spent grain, now protein-rich but sugar-poor, is conveyed out of the system. Many large breweries donate or sell this grain to farms as cattle feed. Next is the boil. In towering stainless steel kettles, the wort is brought to a rolling boil and held there for 60 to 90 minutes. This step sterilizes the liquid, halts enzymatic activity, and causes unwanted proteins to coagulate and fall out of suspension. It's also when hops are added. Hops are the cone-shaped flowers of the Humulus lupulus plant, prized for their bitterness, flavor, and aromatic oils. In a factory setting, hops usually arrive as compressed pellets for consistency. Early additions bring bitterness. Late additions and whirlpool hops contribute aroma and flavor. Boiling is carefully managed. A powerful steam jacket heats the vessel, while a system of condensers captures volatile compounds and steam vapor to reduce environmental impact. The smell during this stage is unmistakable. Sharp, herbal, sweet, and slightly pungent. It's the moment beer begins to take on its final character. After the boil, the wort must be rapidly cooled. This happens in a plate heat exchanger, where hot wort flows past cold water or glycol in alternating metal plates. Temperatures drop from near boiling to fermentation ready, usually between 10 degrees Celsius and 20 degrees Celsius, in just seconds. In most large breweries, the water used to cool the wort is captured and reused to preheat the next batch, conserving energy. From there, the chilled wort is transferred to fermentation tanks, colossal, conical bottom vessels made of polished stainless steel. Some are the size of small buildings. This is where the magic really happens. Yeast is introduced, either ale yeast or lager yeast. Yeast begins feeding on the sugars in the wort, producing alcohol and CO2 as byproducts. The tanks are fitted with sensors that monitor temperature, pressure, and gravity in real time. If fermentation is too vigorous, pressure is vented. If it's too slow, temperature can be nudged to wake up the yeast. Fermentation can last from a few days for ales to several weeks for lagers. During this time, brewers pull samples to test for alcohol levels, residual sugars, pH, and flavor development. In big factories, this data is fed into digital brewing systems that model yeast health and fermentation curves. If something's off, brewers are alerted immediately. Once fermentation is complete, the beer isn't quite ready. It must be conditioned, held at near freezing temperatures to clarify and stabilize. During this stage, yeast settles out, flavors mellow, and carbonation levels are adjusted. Some factories use centrifuges to speed clarification. Others rely on time and gravity. Filtration may be employed, either with diatomaceous earth, membranes, or cross-flow systems to remove fine particulates and ensure brilliant clarity. For beers that are meant to be bright and shelf-stable, pasteurization may follow, either flash pasteurization or tunnel pasteurization. But not all beer is pasteurized. Many craft style or draft-only products skip this step to retain delicate aromas. Once the beer is bright, cold, and stable, it's ready for packaging. In large breweries, packaging lines are like choreographed metal highways. Bottling lines can run at 1,200 bottles per minute. Can lines are even faster. Kegs are cleaned, filled, capped, and labeled by machines. Bottles are rinsed, filled under pressure to avoid foaming, sealed with crown caps, and passed through date coders and labelers. Cans are seam locked, rinsed, and pressure checked. Every container is sampled for fill height, oxygen pickup, carbonation, and microbial safety. In some facilities, advanced cameras scan every bottle or can for imperfections in milliseconds. The packaging halls are cold, loud, and almost hypnotic. Conveyor belts twist and curve. Robotic arms stack cases onto pallets. Shrink wrap machines seal entire loads for distribution. Forklifts or automated guided vehicles shuttle product to cold storage, where beer awaits distribution to bars, grocery stores, sports stadiums, and corner shops around the world. But behind the machinery is a deeper layer of quality assurance. Beer is a living product, and even at massive scale, breweries run labs that would rival pharmaceutical facilities. There are microbial labs, sensory panels, gas chromatographs, and mass spectrometers analyzing aroma compounds, esters, sulfur levels, and oxygen ingress. Trained tasters, often called sensory analysts, taste beer daily, blind, and score it against reference samples. A slight change in carbonation or hop aroma is enough to flag a batch for review. And hygiene is non-negotiable. Brewing equipment is cleaned constantly with clean-in-place systems that circulate caustic solutions, acid rinses, and sanitizers through every pipe, pump, tank, and valve. Breweries are designed with sloped floors, airlocks, positive pressure rooms, and filtered ventilation to minimize contamination. Yeast cultures are kept in pure, cryogenically preserved banks and propagated in sterile fermenters. Even the water is treated, filtered, softened, and dechlorinated to ensure it doesn't introduce off flavors. Despite the scale, there's a strange elegance to the whole system. Every tank, pump, sensor, and pipe is part of a carefully designed loop. From raw grain to finished beer, the factory operates almost like an ecosystem, closed, balanced, and tightly monitored. Nothing is left to chance. Even the CO2 released during fermentation is often captured and reused to carbonate the final product, reducing waste and environmental impact. Bacardi all starts with molasses, a byproduct of sugar refining. Once cane juice has been boiled and crystallized into sugar, what remains is a dark, viscous liquid rich in residual sugars and minerals. Bacardi sources its molasses primarily from the Caribbean and Central America, where sugarcane grows in abundance. Shipments arrive by the ton, offloaded into deep storage tanks that keep the molasses warm and pumpable. Its smell is rich and heavy, deeply sweet, slightly sour, with a roasted, almost smoky undertone. Before fermentation begins, the molasses is diluted with pure water and combined with nutrients to prepare what's known as the fermentation wash. Bacardi uses a proprietary strain of yeast, one that's been carefully preserved and propagated for generations. This yeast is key. It's what gives Bacardi its distinctive profile: clean, light, with subtle fruity esters and very low levels of fusel oils. In a dedicated propagation room, yeast cells are grown in increasingly larger vessels, fed on molasses and oxygen, until they're strong enough to handle full-scale fermentation. The prepared wash, diluted molasses, nutrients, and yeast is pumped into fermentation tanks, towering steel vessels the size of small silos. Fermentation is fast and efficient, typically 24 to 30 hours. During that time, the yeast devours the sugars, converting them into alcohol and CO2. The temperature is carefully regulated. Too hot, and the yeast dies. Too cold, and it underperforms. Sensors monitor every parameter in real time: sugar levels, temperature, pH, alcohol content. In massive control rooms, technicians watch digital dashboards as each tank ferments with machine-like consistency. The result of this stage is not rum yet. It's a low alcohol liquid called wash or beer, usually around 7 to 10% ABV. It smells nothing like rum. It's sweet, funky, raw. To transform it into the clear, potent spirit known around the world, Bacardi moves to the next phase: distillation. Distillation is where alcohol is concentrated and flavors are defined. Bacardi doesn't rely on pot stills, as many small batch rums do. Instead, it uses continuous column stills, tall, multi-stage distillation towers that can separate alcohol with incredible precision. These columns have trays or packing materials inside that force the vapor and liquid to interact repeatedly, concentrating the alcohol while removing unwanted compounds. The fermented wash is pumped into the column, heated from the bottom, and as it rises, different components evaporate at different heights. Light, clean alcohols rise to the top and are collected. Heavier compounds are left behind and drained off. By adjusting the temperatures and reflux ratios, Bacardi's distillers control the exact cut of alcohol they want to keep. The result is a high-strength spirit, often 85% ABV or higher, that's clear, light, and extremely pure, essential for Bacardi's signature smoothness. But pure alcohol isn't rum yet. The next steps, aging, blending, and finishing, are where the artistry comes in. The raw distillate, also called aguardiente, is diluted down to around 60 to 70% ABV and pumped into oak barrels for aging. Bacardi primarily uses used American white oak barrels, many of which once held bourbon. These barrels are charred on the inside, and over time, they impart color, vanilla notes, spice, and tannins to the rum. In Bacardi's aging warehouses, massive barrel halls with racks stacked to the ceiling. Tens of thousands of casks rest in the tropical heat. The climate speeds the interaction between spirit and wood, making even short aging periods highly effective. Different rums are aged for different durations. Bacardi Superior, the classic white rum, may be aged for as little as 1 year before being filtered. Gold and flavored varieties rest longer. Premium products like Bacardi 8 or Bacardi Reserva Limitada are aged 8 to 12 years or more. Each barrel breathes. Alcohol evaporates, a phenomenon known as the angel's share, and oxygen seeps in. Over time, harsh edges soften, flavors deepen, and the rum becomes increasingly complex. Once aging is complete, barrels are emptied, and the rum is evaluated. This is where Bacardi's master blenders, trained experts who can detect flavor differences down to the subtlest note, step in. Dozens, sometimes hundreds of barrels are selected and blended together to create a final product with exactly the right profile. Some rums bring fruity notes, others deliver weight or spice, others still provide structure or sweetness. The blender's job is to make the sum better than the parts, and to ensure that every bottle tastes exactly like the last one, year after year. Now comes one of Bacardi's most distinctive processes: charcoal filtration. For Bacardi Superior and other light rums, the blended rum is passed through layers of activated charcoal, often made from coconut husks, to remove color and certain heavy flavor compounds. This process, inspired by Don Facundo Bacardi himself in the 1860s, strips away rough edges and leaves the rum bright, clean, and smooth. Even after aging in oak, the charcoal returns the rum to a near-clear appearance while preserving its vanilla and almond undertones. Once filtered, the rum is diluted with ultra-pure demineralized water down to bottling strength, usually 37.5% or 40% ABV, depending on the market. It's then passed through fine mesh filters to remove any remaining particles, chilled to encourage clarity, and tested for stability. Quality checks are constant. ABV, color, turbidity, aroma, flavor, all are measured in both labs and sensory rooms. Finally, the rum is ready to be bottled. Bacardi's bottling lines are massive, high-speed operations, capable of producing tens of thousands of bottles per hour. Empty glass bottles, custom-shaped with embossed bats and logos, are automatically loaded onto conveyors. They're rinsed, filled with rum under pressure, sealed with tamper-proof caps, and labeled with laser precision. Date codes are printed, barcodes are verified. Every bottle passes through inspection tunnels equipped with cameras and sensors to catch defects, underfills, or misplaced labels. From there, bottles are packed into cartons by robotic arms and shrink-wrapped onto pallets. Pallets are barcoded, logged, and stacked in warehouse zones ready for distribution. Bacardi's logistics network spans continents. From a single facility, trucks, ships, and containers move product across the globe to supermarkets in Spain, beach bars in Brazil, nightclubs in New York, and resorts in Thailand. Behind the scenes, sustainability plays an increasing role. Many of Bacardi's distilleries use renewable energy, recycle processed water, and recover CO2 from fermentation. Spent yeast and distillation byproducts are often converted into animal feed or used in bioenergy systems. Even the barrels, when retired, may be repurposed for furniture, flooring, or smaller barrel aging projects. Waste reduction is not just about economics. It's part of preserving the legacy of the land and the product itself. And yet, for all this technology and scale, Bacardi's rum still carries with it a certain history, a sense of origin. The company was founded in 1862, and though exiled from Cuba in the 1960s, its roots remain in the tropics. The smoothness of Bacardi rum isn't just a technical achievement, it's a philosophy. Every step, from selecting molasses to filtering the final spirit, is guided by an obsession with drinkability. A Bacardi rum should be mixable, approachable, and endlessly clean on the palate. Jack Daniel's begins with a precisely controlled mash bill of 80% corn, 12% malted barley, and 8% rye. The grains arrive in massive quantities by rail and truck, and are stored in silos before being milled on-site in Lynchburg, Tennessee. Corn is cracked into coarse grits. Malted barley and rye are milled finer. The grain is moved pneumatically into huge stainless steel cookers where it undergoes a staged cooking process. Corn first, cooked at a high temperature to gelatinize the starches, then rye, then finally malted barley is added as the mash cools to around 65 degrees Celsius. The malt's enzymes convert starches into fermentable sugars. The resulting mash is pumped into one of 64 fermentation vats. Open-top tanks made from cypress wood, some more than 80 years old. These vats each hold around 40,000 gallons. Jack Daniel's uses its own proprietary yeast strain, maintained and propagated internally since the early 20th century. Before yeast is pitched, a portion of the previous day's fermented mash is added to the new batch. This sour mash technique helps control the pH and microbial stability of the fermentation environment. Yeast is pitched in liquid form and begins consuming sugars, producing ethanol and CO2. Fermentation lasts 4 to 6 days. The mash foams, bubbles, and gives off heat. During peak fermentation, tanks require constant monitoring for overflow and contamination. Automated sensors track sugar depletion, CO2 output, and temperature curves. Staff monitor the aroma, foam height, and microbial activity daily. When fermentation is complete, the liquid contains roughly 7-9% alcohol by volume. This distiller's beer is pumped into column stills, massive stainless steel and copper columns more than 40 feet tall. Jack Daniel's uses a single-stage continuous distillation process. Beer enters the column at various levels, while steam is injected from below. Alcohol vapor rises, separating from heavier components. The alcohol vapor is routed to a doubler, essentially a pot still operating at atmospheric pressure, where it's condensed, reheated, and distilled again. The resulting clear spirit, often referred to as white dog, emerges at around 140 proof. Before aging, Jack Daniel's performs its most defining step, the Lincoln County process, or charcoal mellowing. This process takes place in vats over 10 feet tall, filled with sugar maple charcoal. The charcoal is made on-site by stacking 2x 2-inch thick maple planks into long rows, igniting them with high-proof whiskey and letting them smolder until fully carbonized. Once cooled, the charcoal is ground into chunks and loaded into mellowing vats. The white dog is slowly trickled, drip by drip, through 10 feet of charcoal, taking 4 to 5 days to pass completely through. The charcoal removes fusel oils, aldehydes, and other harsh flavor compounds. The process is gravity-fed and unpressurized, requiring a consistent flow rate to maintain quality. The resulting spirit retains its proof, but emerges smoother and cleaner, with noticeably reduced volatility. Once mellowed, the whiskey is moved into new, charred American white oak barrels, coopered at Jack Daniel's own barrel-making facility. The staves are air-seasoned outdoors for 6 months to 2 years, then assembled, toasted, and flame-charred to a specific level designed to maximize flavor extraction and color development. Each barrel holds about 53 gallons. The inside is blackened from charring, and the wood sugars have caramelized. Barrels are filled at 125 proof and rolled into one of 90-plus barrel houses across the Lynchburg area. These rickhouses vary in size and construction. Some are multi-story wood frame structures, others are steel-clad, but all use passive temperature variation to promote aging. Inside the barrel house, environmental conditions vary dramatically. Upper floors reach 100-degree F+ in summer, encouraging evaporation and faster aging. Lower levels remain cooler and more stable. Jack Daniel's does not rotate barrels between floors, so aging is not uniform. Instead, blending later equalizes the flavor profiles. Barrels are stacked on wooden ricks, often 6 to 7 high. During aging, the whiskey interacts with the wood. Alcohol penetrates the staves, extracting vanillin, lignin-derived compounds, tannins, and hemicellulose breakdown products like caramelized sugars. Oxidation occurs gradually as oxygen seeps through the porous wood. Angel's share evaporation causes the proof to rise over time and concentrates the flavor. Each year, a barrel loses 2-5% of its volume to evaporation. Maturation time varies by product. Old No. 7 typically ages for 4 to 6 years. Higher end expressions like Single Barrel or Sinatra Select may rest for up to 8 years or more. Throughout aging, barrels are sampled periodically. Staff draw whiskey using a thief and assess it by color, aroma, proof, and mouthfeel. No age statement is printed on standard Jack Daniel's because blending is used to maintain consistency, not target a specific age. When deemed mature, barrels are dumped onto a stainless steel trough, filtered through mesh screens to catch char, and moved to batching tanks. Here, up to 200 barrels are blended into a single batch. Before bottling, the whiskey is chill filtered, cooled to near freezing, and passed through paper or cellulose filters to remove fatty acid esters that can cause clouding in the bottle. For Old No. 7, The spirit is then diluted to 80 proof, using demineralized water drawn from the same cave spring used for mashing. Other products, like bonded or single barrel proof, may be bottled at higher strengths or without filtration, depending on the release. Bottling takes place on high-speed automated lines. Empty bottles are rinsed with pressurized air or filtered water. Filling machines dispense whiskey using gravity-fed nozzles or vacuum-assisted pumps. Bottles are capped with aluminum closures, corks, or synthetic caps depending on the SKU. Labels are applied using roll-fed labelers with electronic eyes that verify positioning. Lot codes and production dates are printed in UV ink or laser etched onto the neck. Every bottle passes under fill level sensors and automated cameras. Defective units are ejected immediately. Bottles are grouped into cases, shrink-wrapped, and palletized by robotic arms. Finished goods are transported to climate-controlled warehouses. Logistics teams track SKU distribution globally. Jack Daniel's is shipped to more than 170 countries. Each batch must meet regional regulatory standards. Export whiskey may require separate bottling or labelling runs to comply with EU, UK, or Asian labelling laws. Quality control labs sample bottles from each run and perform gas chromatography and spectrophotometry to confirm chemical composition. Sensory analysts run blind tastings daily to validate flavour accuracy. Any deviation from the flavour profile, too much wood, too much sweetness, excessive ethanol burn, results in a hold or rework. Spent grain from mashing is pumped to presses, dried, and sold as cattle feed. Wastewater is treated on-site using anaerobic digesters and aerobic ponds before being discharged or reused. Energy recovery systems capture steam from cooking and distillation to heat water for fermentation tanks. Charcoal from the mellowing vats is replaced regularly and either regenerated or disposed of as biomass fuel. Spent barrels are sold to Scotch distilleries, hot sauce producers, and breweries for secondary use. The cooperage also reconditions barrels for use in cask-finished products or special editions. The distillery operates under strict federal and state regulation. Every barrel and bottle is tracked with a unique serial number. Auditors inspect warehouse records, bottling logs, and inventory counts. The distillery maintains TTB-compliant records for every production step, from raw grain receipt to final export certificate. Barcodes and RFID tags on pallets ensure traceability from distillation to retail shelf. Security is tight, bonded warehouses are sealed, and access is controlled. Jack Daniel's uses SAP-based systems for production scheduling, batch tracking, and global inventory management. Brewing, fermentation, and distillation data are logged automatically by PLCs connected to SCADA systems. Operators monitor process parameters in real time on touchscreen interfaces. Alerts are triggered if mash temperature, fermenter pressure, still output, or bottling line speed moves out of range. Scheduled maintenance is performed weekly. Sensors check flow rates, valve positions, CIP cycle effectiveness, and tank volumes continuously. Yeast propagation is handled in a sterile lab with HEPA-filtered air, jacketed tanks, and strict aseptic technique. Each batch of yeast is cryogenically preserved and banked in long-term storage. Lab staff test yeast for viability, contamination, and fermentation performance. Infection events, such as wild yeast or lactic acid bacteria, are rare but can halt production for full CIP sanitization of all affected equipment. Sanitizers include caustic soda, peracetic acid, and steam. Safety inspections and confined space protocols are rigorously enforced, especially around fermentation tanks, high-pressure steam lines, and ethanol vapor zones. Mash cookers and fermentation tanks are cleaned between every batch. Distillation columns are stripped and acid washed quarterly. Mellowing vats are emptied and replenished every few months. Barrels are inspected for leaks before filling. Leakers are flagged and re-cooped or discarded. Every floor drain, gasket, and pump seal is part of a scheduled inspection checklist. The entire facility is USDA certified for food safety and operates under HACCP protocols. Salmon production begins immediately after harvesting with rapid transport of whole fish to processing facilities. The fish are received in chilled holding tanks or insulated containers with ice slurry, where temperature is maintained near 0 degrees Celsius to minimize enzymatic activity and microbial growth. Once unloaded, the fish are fed into a de-icing flume system, where circulating chilled water removes surface ice and any external debris. After de-icing, fish are conveyed by stainless steel belt or pneumatic water transport to the grading station. Grading machines use load cell equipped conveyor belts or camera-based systems to categorize each salmon by weight class and body dimensions. Size data is recorded and used to assign each fish to a specific processing line depending on target product specifications. Following grading, salmon are transferred to stunning and bleeding stations. Here, automated percussive or electrical stunning devices render the fish unconscious in under 1 second. Immediately after stunning, a rotary knife or fixed blade system incises the gill arch. The fish then enter a bleeding tank or conveyor where they are held for 5-10 minutes in chilled water to drain blood via circulatory pressure, improving flesh appearance and shelf life. Next is deheading and gutting, where fish are positioned by automated orientation systems to align uniformly before high-speed rotary blades remove the head. The carcasses pass through a ventral incision machine where circular or V blades open the abdominal cavity. Viscera are extracted using vacuum suction nozzles or mechanical scrapers. Internal membranes are further removed by pressurized water jets aimed at the peritoneal cavity. A water flusher system removes residual debris. Eviscerated salmon proceed to the trimming section, where trained operatives or automated vision-guided blades remove the kidney line, dorsal fin remnants, and any remaining membrane tissues. Machine-assisted trimming modules use camera detection and robotic knives for precision cuts at high speed. Visual scanners inspect the cavity for any leftover material. After trimming, fish are re-washed using chilled, potable water from multiple spray nozzles. Washed carcasses are fed into a filleting machine. This equipment uses belt-fed positioning and blade pairs to cut along the spine, separating the two fillets. These blades are height adjusted based on pre-scanned fish dimensions to ensure optimal yield. The resulting fillets are guided into discharge lanes, while frames and collars are diverted to co-product processing. Post-filleting, fillets move to a pin bone removal station. This step is performed using mechanical bone pullers with rotating rubber wheels and suction extraction. The system identifies bone position based on predefined muscle anatomy and removes intermuscular bones without damaging the surrounding flesh. Depending on line setup, bone removal can also be conducted manually with tweezers for premium products. Fillets then pass through trimming belts, where tail tips, belly flaps, collar edges, and skin tears are removed. Trimming can be configured based on customer specification. Camera-based sorting systems ensure uniformity, and deviations trigger diverters to reroute products for manual correction. The next stage is skin removal. Skinning machines feed fillets into a blade interface that separates the skin from muscle while minimizing meat loss. Blade pressure, feed rate, and depth of cut are adjusted via servo control systems. Some processing lines retain the skin for specific markets or product forms. After skinning, fillets are conveyed to portioning systems. Portioning is carried out with water jet cutters, ultrasonic blades, or mechanical slicers. Laser-guided mapping scans the fillet to define weight and shape. Cutting systems then divide the fillet into precise portions according to program parameters, such as fixed weight steaks, loins, or saku blocks. Cut portions are collected in synchronized lanes for immediate packing. In parallel, whole fillet lines bypass the portioning system. These fillets are passed through grading systems based on fat line visibility, color, and size. Multi-sensor units evaluate each fillet with color cameras, near-infrared sensors, and weight scales. Graded fillets are sorted into categories and routed accordingly. Chilling is applied before packaging. Fillets and portions are passed through a spiral or tunnel chiller where they are cooled with cold air or flaked ice mist to reduce core temperature to below 2 degrees Celsius. Chilling units use digital thermostats and humidity sensors to maintain consistent internal environment and airflow. Once chilled, the product enters the packaging zone. Here, fillets and portions are loaded into trays or vacuum pouches. Modified atmosphere packaging is commonly used, where oxygen is displaced and replaced with CO2 and N2 in precise ratios to extend shelf life. Gas mixtures are controlled by flow meters and validated with gas analyzers. Trays are sealed with lidding film using heat sealing units that ensure proper adhesion and headspace control. Vacuum packaged products are loaded into form-fill seal machines, which mold film around the product, evacuate air, and seal the pack in a continuous motion. Vacuum level, seal time, and film tension are PLC controlled. Pack integrity is tested using pressure decay sensors or inline leak detection systems. After packaging, units proceed to labeling and coding. Print and apply labelers affix product labels with weight, species, origin, and batch codes. Inkjet or laser coders apply best before dates and traceability codes on film or trays. Optical scanners verify label placement and print clarity. Packaged products are then grouped into secondary packaging units. Collating conveyors align packs for insertion into cartons or crates. Case packers load these into pre-formed boxes. Automated box sealers apply tape or glue to secure the cartons. Tertiary barcodes are printed for shipping and scanned for inventory integration. Sealed boxes are routed to palletizing cells. Robotic palletizers stack boxes according to predefined patterns using vacuum heads or fork grippers. Pallets are wrapped with stretch film and labeled with shipment data. Each pallet is scanned and assigned a warehouse location in the inventory management system. Cold chain is maintained throughout with temperature sensors on conveyors, in holding rooms, and inside chilling units. Deviations trigger alerts and system flags. Data is logged and linked to each batch for traceability. End product temperatures are sampled using calibrated probes to verify compliance. Co-product handling operates in parallel. Salmon heads, frames, belly trims, and skin are collected separately. Heads and frames are directed to fish meal or oil extraction. Trimmed bellies may be sorted for smoking or mincing. Skins are graded and can be air-dried or frozen for export. All co-products are processed using stainless steel conveyors, crushers, or mincers with washdown capability. Smoking lines, if present, begin with brining or dry salting. Fillets are conveyed to tumblers or brine tanks, where salt concentrations and immersion time are automated. After salting, fillets are dried in humidity-controlled rooms before entering the smokehouse. Smoke is generated from wood chips or liquid smoke atomizers. Parameters such as smoke density, temperature, and air velocity are digitally controlled. After smoking, fillets are cooled and sliced using parallel slicers calibrated for thickness. In freezing operations, portions or fillets are directed to spiral freezers or contact plate freezers. Products are loaded onto stainless steel belts that pass through cold chambers at -35 degrees Celsius to -45 degrees Celsius. Dwell time is adjusted for product thickness to reach core temperatures below -18 degrees Celsius. Frozen products are bagged and sealed before moving to cold storage. Steak production begins after the animal carcass is chilled post-slaughter. Carcasses are held in cold storage rooms at 0 degrees Celsius to 2 degrees Celsius for 24 to 48 hours to complete rigor mortis and stabilize muscle structure. After this phase, the chilled sides are moved to the fabrication area using overhead rail systems equipped with trolleys. The first step is primal cutting. Sides of beef are placed on breaking tables and cut into primal sections using bandsaws and large breaking knives. The carcass is separated into forequarter and hindquarter at the 12th and 13th rib. The forequarter includes the chuck, brisket, rib, and plate, while the hindquarter contains the loin, round, and flank. From the hindquarter, the loin primal is isolated, which contains the strip loin, tenderloin, and short loin, common sources for high-grade steak cuts. The rib primal from the forequarter contains the ribeye section. Each primal is weighed, tagged with traceability information, and placed into designated bins or hooks. Primal sections are then moved to the boning line. Here, trained operators or automated knife systems remove bone structures. For ribeye and strip loin, the chine bone, feather bones, and spinal processes are removed using powered wizard knives or mechanical boning blades. Tenderloins are peeled away from the lumbar region with membrane knives, preserving the natural shape and minimizing yield loss. After deboning, cuts proceed to surface trimming, where external fat, silver skin, and connective tissues are removed. Precision trimming is performed using hand tools or vision-guided trim robots. Final trim levels are determined by target specifications, such as 1 4-inch fat cap or lean trim. The trimmed subprimals are transferred to aging rooms or directly to portioning, depending on the program. If aged, subprimals are vacuum packed using thermoforming machines and stored under controlled conditions at 0 degrees Celsius to 2 degrees Celsius for wet aging. Typical wet aging periods range from 14 to 28 days, depending on product line. Aged subprimals are retrieved and conveyed to the portioning area, where they are unpacked and visually inspected. Excess purge is drained, and the product is patted dry if needed to ensure consistency during slicing. Subprimals are loaded onto scanning tables equipped with 3 D-laser or X-ray systems. These systems analyze dimensions, fat distribution, and muscle structure to optimize cutting paths. Based on scan data, subprimals are transferred to automated steak portioning machines. These use rotating circular blades or water jet cutters to slice steaks at consistent thickness and target weight. Blade systems are servo-controlled to adjust angle and pressure in real time, compensating for shape variability. Common cut configurations include ribeye steaks, strip steaks, T-bone, porterhouse, sirloin, filet mignon, and top blade flat iron. Each type is portioned according to thickness specifications, typically ranging from 12 mm to 38 mm, and target weight tolerances within ++ 1%. Cutting yield and number of steaks per subprimal are calculated live by onboard processors. Each steak is then conveyed to a weighing and grading station. Individual steaks pass over in-motion scales to confirm net weight. High-resolution imaging systems evaluate marbling score, surface integrity, and lean color. Grading software assigns visual quality rankings, and steaks are automatically sorted into output lanes based on specification match. Steaks requiring tenderization are routed through mechanical tenderizing machines. These consist of rotating blade rollers that pierce the muscle to sever connective fibers without altering surface appearance. For certain cuts like top round or sirloin, multiple passes may be used to reach the desired tenderness level. At this stage, enhancement or marination systems can be applied. For value-added products, steaks are loaded into vacuum tumblers or injector systems. Vacuum tumblers rotate the meat with liquid solution containing water, phosphate, salt, and flavoring. Injectors use multi-needle heads to evenly distribute brine through muscle fibers at defined pickup rates. Enhanced steaks are rested in staging bins for a defined soak period, then reweighed to verify target pickup has been achieved. Stricter control is maintained for fixed weight packs, where brine gain must fall within narrow tolerances to avoid over or under packaging. From here, steaks are conveyed into the packaging line. For fresh retail presentation, steaks are placed into polystyrene trays with absorbent pads and conveyed under MAP systems. Trays enter a sealing unit where oxygen is displaced with gas mixtures and overwrapped with clear lidding film. For vacuum-sealed steaks, portions are transferred to form-fill-seal machines. In these systems, bottom web film is thermoformed into pockets, steaks are loaded manually or robotically, and top film is vacuum sealed over the product. Seal bars apply pressure and heat to ensure consistent seal quality. Vacuum sealed steaks, intended for frozen distribution, are routed immediately to spiral or plate freezers. Steaks are individually frozen to core temperatures below 18 degrees Celsius in 30-60 minutes, depending on thickness. Frozen steaks are then bagged or boxed in bulk, with barcode labels applied for inventory tracking. Finished packs pass through metal detection and weight verification systems. Inline metal detectors scan for stainless, ferrous, or non-ferrous contaminants, rejecting non-conforming packs. Checkweighers confirm that net weight falls within compliance range. Data is logged to the MES system and linked to batch production ID. Packs are labeled with product name, weight, grade, origin, and expiry using thermal inkjet printers or automatic label applicators. Optical sensors ensure correct label application, alignment, and data accuracy. Invalid or missing labels trigger rejection and pack removal. Labeled steaks are grouped using robotic case packing systems. Retail packs are placed in corrugated shippers or RPCs, arranged according to order profiles. Case formers and glue applicators prepare cartons, which are sealed and labeled with GTIN, lot, and dispatch codes. Cases are moved to palletizing stations, where robotic arms stack them into predefined patterns on wood or plastic pallets. Pallets are then wrapped in stretch film for load stability and scanned into inventory management systems. Each pallet is assigned a location in chilled or frozen storage, depending on product type. All processing zones are monitored with environmental sensors. Temperature, humidity, and air velocity are logged continuously. Conveyor speeds, blade RPMs, cut counts, and yield rates are tracked via PLCs connected to a central SCADA system. Downtime, throughput, and machine error logs are accessible in real time. Quality assurance procedures include destructive sampling and analytical testing. Random steaks are removed and evaluated for marbling score, thickness, weight accuracy, pH, water holding capacity, and sensory characteristics. Steaks are cooked under controlled conditions to assess texture, flavor, uniformity, and juiciness. Chicken strip production begins with the reception of chilled, deboned chicken meat, typically composed of boneless breast fillets. These are transported in bulk containers from upstream slaughter and deboning facilities. On arrival, the meat is inspected for temperature compliance, then tipped into stainless steel hoppers for transfer into the cutting line. Chicken fillets are conveyed to the portioning section, where they are aligned on belts and scanned by high-resolution cameras coupled with laser or X-ray systems. These scanners detect size, shape, and internal structure. Data is processed in real time to guide water jet or blade-based cutters that slice each fillet into uniform strips based on predefined weight, length, and thickness tolerances. Strips are conveyed into a trimming and inspection zone. Here, off-spec pieces, connective tissue, and surface fat are removed by automated blade systems or manually trimmed depending on the processing setup. A secondary vision system performs quality control on the stripped portions, ejecting defective pieces using pneumatic nozzles. Trimmed strips move into the marination system. The marination line consists of tumbling drums or vacuum massages. Strips are loaded into the drum, which rotates while marination solution is injected or poured in. Marinade is typically a blend of water, salt, phosphates, modified starches, and flavor compounds. Ingredient mixing tanks feed the drum with chilled solution via peristaltic or centrifugal pumps. Drums operate under partial vacuum or atmospheric pressure depending on marination type. Vacuum assists protein extraction and enhances moisture retention. Tumbling speed and duration are controlled digitally, typically operating at 612 revolutions per minute for 15, 25 minutes. Finished marinated strips are discharged onto dewatering belts to remove excess surface marinade. Moisture-adjusted strips are conveyed into the coating system, a multi-stage line that applies a breading or batter system to each piece. The first stage involves pre-dusting, where strips are evenly coated with dry flour or modified starch powder to improve batter adhesion. Pre-dusting is applied via vibratory sifters and curtain feeders with excess powder removed by air blowers. Coated strips proceed to the battering station, where they pass through a liquid bath consisting of water, wheat flour, leavening agents, gums, and spices. Batter is recirculated continuously through inline filtration and agitation systems to maintain uniform viscosity. Strips are submerged using conveyor paddles, then raised through a vibrating belt to allow excess batter to drip off. Next is the breading application. Strips are dropped into a bed of dry breading mix, which may consist of breadcrumbs, cornmeal, or tempura crumbs. Top and bottom conveyors press breading into the meat surface. Breaders feature reflow systems that recirculate unused coating material after sifting out fines. Compressed air jets remove excess coating. For products requiring double coating, the batter and breading stages are repeated with a secondary set of machines, typically using coarser crumb materials for texture variation. Each station is monitored for line speed, dwell time, batter pickup, and breading adhesion. Strips then enter a setting fryer or pre-fry system. The setting fryer contains oil heated to 180-200 degrees Celsius and is typically 10-30 seconds in duration. This step partially cooks the outer coating to fix structure and prevent loss during freezing. Fryer oil is continuously filtered and circulated to maintain clarity. Exit temperature and surface moisture are measured in line. Post-fry, strips are transferred to a cooling conveyor that uses forced ambient or chilled air to reduce product temperature to under 30 degrees Celsius. Cooling prevents condensation in the next stage and prepares the surface for freezing. Conveyors are made of mesh belts for air penetration. Air velocity and temperature are controlled to stabilize product dimensions. Cooled strips are arranged in rows and conveyed into the freezing tunnel. Spiral or linear IQF freezers are used. Inside the tunnel, product is exposed to high velocity air at temperatures between 35 degrees Celsius and 45 degrees Celsius. Belt speed and airflow are calibrated to bring the product core temperature below 18 degrees Celsius within 15-25 minutes. IQF technology ensures each strip remains separate by using belt vibration, cryogenic burst, or pre-chill alignment. Ice accumulation and belt defrosting are controlled via automated heat pulse cycles. Tunnel freezers are cleaned in place and monitored for temperature uniformity. Once frozen, strips enter the weighing and sorting station. Multi-head weighers mounted above packaging lines portion strips into programmed weight ranges. Optical or X-ray systems recheck for foreign materials, bone fragments, or density anomalies. Rejected product is diverted automatically. Weighed portions drop into bags or trays using form-fill seal equipment. For pillow bags, film is pulled from rolls, formed into a tube, filled with product, and sealed at the top and bottom by heated jaws. For tray packs, plastic trays are filled and lidded with sealed film using MAP systems, replacing ambient air with nitrogen and carbon dioxide. Each pack is labeled with product ID, batch number, and expiration using inkjet printers or label applicators. Vision systems confirm label placement and code legibility. Weighed packs are verified for target range and conveyed to check weighers. Under or overweight packs are removed via pneumatic rejectors. Packaged units are collated and loaded into cartons. Carton erectors fold and glue cases, while robotic arms load a fixed number of bags or trays per box. Cartons are sealed, labeled, and scanned for tracking codes. Logistics data is applied using print and apply labelers that communicate with the plant's ERP system. Boxes are transferred to robotic or gantry-style palletizers. These systems stack cases on wooden or plastic pallets in staggered patterns to optimize height and weight distribution. Pallets are stretch-wrapped using rotary arm or turntable wrappers. Finished pallets are tagged with shipment barcodes and stored in cold storage warehouses maintained at 20 degrees Celsius. All processing stages are monitored by a PLC integrated SCADA system. Control points include marination pump flow, batter viscosity, breading density, fryer oil temperature, freezer airspeed, and packaging line synchronization. Recipe management software ensures every batch conforms to target formulation and processing times. Sensor data is collected from load cells, thermocouples, optical sensors, belt encoders, and pressure gauges. Line operators access live performance dashboards from HMIs to monitor throughput, reject rates, and downtime per station. Alarms and parameter deviations are logged in the plant MES. Quality assurance involves sample testing at key stages. Strip dimensions are measured post-cutting with digital calipers. Batter pickup percentage is calculated by weight differential before and after coating. Oil content is checked using Soxhlet extraction post-fry. Internal temperature is verified post-freeze using calibrated thermometers. Microbial samples are taken from finished product and contact surfaces. Swabs are tested for total plate count, Listeria SPPER, and Salmonella SPP. Moisture, protein, and fat levels are confirmed via NIR spectroscopy or gravimetric methods. Product consistency is tracked against batch specifications. Yield data is compiled for raw input versus packaged output to monitor efficiency. Trimming loss, batter loss, breading recycle rates, and oil usage per kilogram of product are calculated for cost optimization. Rework loops return trimmings and off-spec strips to reprocessing lanes if permitted. It begins with water, ordinary in origin, but transformed through an intense purification system. First, the water flows through mechanical filters, stripping out any visible particles. It moves next into activated carbon beds, where chlorine, organic residues, and odors are removed. Then it's pushed through reverse osmosis membranes under high pressure, leaving behind salts, microbes, and trace contaminants. A final sweep of ultraviolet light and ozone leaves the water sterile, mineral-free, and chemically neutral. This is the blank canvas. The next stage injects character. Deep inside jacketed mixing tanks, a thick amber concentrate is created. Liquid sugar surges through stainless steel lines into the tank, met by metered doses of colorants, acids, caffeine solution, and the core flavor compound. Inside the vessel, high-speed impellers shear the mixture into uniformity. The liquid darkens, thickens, and becomes the syrup that defines the drink's signature base. Flow meters and refractometers verify sugar density to the decimal. Agitators spin in controlled bursts. A small shift in temperature or pH would trigger instant correction by the automated control system. Once blended, the syrup doesn't wait. It flows straight into a proportioning unit, where it meets the ultra-purified water. Two pressurized lines merge into one, and precisely tuned valves blend them in a 5:1 ratio. The new mixture forms a complete beverage. Almost. First, it's sprayed into a vacuum chamber. This fine mist encounters low pressure and a cloud of CO2. Oxygen is stripped away. The liquid is chilled rapidly to near freezing, lowering its ability to resist carbonation. Inside the carbonation vessel, thousands of microscopic pores inject CO2 with exact pressure. The liquid churns gently in a sealed chamber, held under 4 bar of pressure at 0 to 2 degrees Celsius. Gas dissolves silently. Bubble size, saturation rate, and temperature are monitored in real time. When carbonation reaches target levels, the drink exits the vessel with all of its effervescence locked in. On another line, PET bottle preforms arrive in rapid succession. Each one is gripped by a rotary arm and passed through infrared heaters. The plastic softens and glows dull red before entering the blow mold cavity. High-pressure air inflates it in a fraction of a second, pressing it against the steel mold's walls to form a full-size bottle, contoured, clear, and warm to the touch. It exits the mold and cools on contact with the conveyor air. Bottles enter the rinsing carousel, where they're inverted and blasted internally with sterilized water. As they flip upright again, air knives dry the insides instantly. Next, they move toward the isobaric filler, a rotary machine that maintains pressure equilibrium between the drink and the container. Each bottle is clamped beneath a filling valve. CO2 gas is injected first to pressurize the empty space. Then the valve opens and the drink enters from the base, rising smoothly with minimal turbulence. Foam is avoided. Gas is preserved. The moment filling is complete, the bottles roll to the capper. Here, precision torque heads spin blue caps onto each neck. A magnetic clutch delivers exact closing force, tight enough to seal, loose enough to open later. Inline torque sensors confirm every closure. Any outliers are ejected instantly by a compressed air nozzle. From there, each sealed bottle passes under a jet printer that marks it with time, date, and batch code. The ink dries in under a second. A vision system verifies code presence and clarity. Another camera checks fill level and cap alignment. Each bottle is under constant scrutiny as it moves down the line at hundreds per minute. Labels come next. A roll-fed applicator unwinds pre-printed film and cuts each label to size. As bottles spin past, a roller applies adhesive, wraps the label, and smooths it with a brush. The result is a seamless, wrinkle-free appearance with perfect alignment. Sensors detect any offset and make micro-adjustments on the fly. Now grouped into formation, the bottles move toward bundling. A collada arranges them into packs, 6, 12, or 24, depending on the format. Shrink film is draped over each group and heat sealed at the seams. The entire bundle then passes through a shrink tunnel where hot air circulates in tight zones. The film tightens instantly, locking the bottles together in a rigid block. Bundled packs exit the tunnel and head for palletizing. Robotic arms swing overhead, guided by vision cameras and programmed stacking patterns. Grippers lift multiple bundles at once and layer them on wooden pallets. Slip sheets are inserted between tiers by a vacuum-fed arm. Once stacked, the entire pallet is conveyed into a stretch wrapper. A rotating arm winds clear film around the stack in tight spirals, binding the load into one secure shipping unit. Meanwhile, cans run on a parallel line. Massive depalletizers feed columns of aluminum cans into a rinsing tower. From there, the empty cans travel into another isobaric filler designed specifically for pressurized metal packaging. Liquid fills the cans from the bottom. A seamer spins down a lid, hooks the metal under the rim, and crimps it tight. A double seam forms, locking the gas inside with extreme precision. Cans are inverted, jet-coated, vision inspected, and shrink-wrapped in trays. Robotic stackers build them into pallet loads at similar speed to the bottle line. Both packaging lines converge in the same warehouse zone, where, Outbound conveyors feed the finished pallets toward refrigerated staging docks. Each section of the line is governed by PLCs. These controllers monitor temperature, fill height, carbonation levels, syrup ratios, and packaging counts. Real-time data appears on SCADA terminals, allowing operators to adjust line speed, diagnose faults, and fine-tune performance without stopping production. If any parameter drifts out of tolerance, such as syrup bricks, carbonation pressure, or label alignment, the system either autocorrects or halts the affected module. Clean-in-place systems activate between product runs. Valves switch flow from production mode to cleaning mode. Heated alkaline solution flushes through all contact surfaces: syrup tanks, filler bowls, carbonators, valves, and pipes. Sensors track flow rate and chemical concentration. After the caustic wash, a water rinse clears residue, followed by a sanitizing flush. No disassembly is required. The entire cleaning cycle is automated and logged. During operation, bottle speeds exceed 60,000 units per hour. Carbonation tanks maintain saturation levels within plus 0.05 volumes. Fill levels are accurate to within plus and 1.5 milliliters. Every step, from syrup blending to cap torque, is governed by tolerances and feedback loops. When the process runs at full speed, hundreds of meters of conveyor synchronize bottle spacing, curve speed, and back pressure control. Star wheels, diverters, and sensors ensure smooth flow with no collisions. Air conveyors keep lightweight empty bottles suspended and aligned without touching mechanical guides. Pepsi's production system is built for non-stop performance. Each component, carbonator, blow molder, labeler, filler, capper, bundler, is modular and servo-driven. Changeovers for different bottle sizes or formats require only a software switch, a tooling exchange, and a calibration cycle. The entire system adapts to new production schedules without downtime. Fanta production starts with water, but it cannot be ordinary. The raw supply flows into a filtration system where coarse particles are stripped away. From there, the water passes through activated carbon beds to remove chlorine and organic traces. Next, it enters a reverse osmosis membrane under pressure, separating out salts, metals, and microbes. At this stage, the water is nearly sterile. A final ultraviolet treatment and ozone injection complete the purification. Now the water is neutral, flavorless, and ready for transformation. Inside a stainless steel mixing tank, the drinks base is constructed. A stream of refined liquid sugar is pumped in through insulated lines. Dosing pumps feed in controlled quantities of citric acid, natural fruit flavors, stabilizers, preservatives, and vibrant colorants. The tank's agitators rotate at set intervals to blend the ingredients evenly. Every element is added with exactitude. Flow meters regulate sugar volume. Acid concentration is tracked by inline pH sensors. Color intensity is verified with optical density readers. The mixture is continuously monitored for consistency. Temperature is held between 15 and 20 degrees Celsius. If any reading deviates from target, the control system halts the process and recalibrates dosing in real time. Once the syrup reaches specification, it is transferred to a buffer tank where it rests briefly under agitation, held at a constant temperature and protected from ambient air. Next, the beverage is formed through a high-speed proportioning system. The syrup is combined with the purified water in a fixed ratio, generally around 1 part syrup to 5 parts water. This is managed by synchronized flow meters and control valves. The blending occurs in line, with turbulence in a stainless steel chamber, ensuring rapid and even mixing. The liquid then flows into a deaeration unit. Inside this sealed vessel, the drink is atomized into fine droplets under vacuum. Dissolved oxygen is extracted while carbon dioxide is introduced. This prevents oxidation, preserves flavor integrity, and prepares the drink for carbonation. Carbonation takes place in a pressurized tank known as the carbonator. Here, the chilled beverage is exposed to a steady stream of carbon dioxide gas. The pressure inside is typically maintained at 3 to 4 bar, and the liquid temperature is kept just above 0 degrees Celsius. These conditions maximize CO2 solubility. Porous stones or fine nozzles distribute the gas, ensuring uniform saturation throughout the tank. Agitators gently rotate to avoid stratification while preventing bubble escape. Meanwhile, packaging lines are activated. If plastic bottles are manufactured on site, polyethylene terephthalate preforms are loaded into a rotary feeder. Each preform is gripped and passed through an infrared heating oven, where the plastic softens. Inside a blow mold cavity, the preform is inflated with high-pressure air into its final shape. Bottles emerge, fully formed and warm to the touch. Air conveyors guide them toward rinsing. Rinsers invert each bottle and spray sterile water into the interior. The bottles are then dried with air knives and positioned upright for filling. They enter a rotary isobaric filler, where pressure is equalized between the bottle and the drink to preserve carbonation. Each bottle is locked into a filling valve. First, carbon dioxide gas purges the empty space, preventing oxygen contamination. Then the valve opens and the carbonated Fanta flows upward from the base. Foam is avoided through bottom-up filling and controlled turbulence. When the fill line is reached, the valve shuts instantly. Excess gas is vented and the bottle is released onto the next conveyor. Caps arrive from a centrifugal sorting bowl. They are aligned, sanitized, and fed toward the capper, where a torque head presses and twists each one onto the bottle neck. The torque is monitored by a feedback sensor that checks every closure in real time. Any bottle that fails to meet torque specs is diverted automatically from the line. A high-speed inkjet printer then marks each bottle with production codes, timestamps, and batch identification. These markings are inspected by vision systems that confirm legibility and placement. Additional cameras check fill height and cap alignment. Bottles failing any inspection are rejected through pneumatic actuators. Labeling follows. A roll-fed labeler applies either pressure-sensitive or glue-applied labels depending on the format. The label roll unwinds, cuts to length, and wraps each bottle in a single smooth motion. Rollers press out any air bubbles, and sensors verify label position. Adjustments are made automatically based on visual feedback. Labeled bottles are grouped into packs at the bundling station. A servo-controlled collator arranges them into 12s, 6s, or 24s depending on product format. A plastic shrink film wraps around the group, and the pack passes through a heat tunnel. Hot air shrinks the film tightly, locking the bottles into a unified pack. The packs move on to palletizing. A robotic arm with suction cups or mechanical clamps picks up each bundle and stacks it on a pallet in alternating patterns. Slip sheets are added for stability. Once a pallet is full, it's moved into a stretch wrapper. A rotating arm wraps plastic film under tension from the base to the top of the stack. This secures the load for transport. Parallel to the bottle line, aluminum cans are processed on a separate track. Empty cans arrive by depalletizer and enter a rinser. After internal cleaning, they flow into a high-speed rotary filler. Isobaric pressure filling minimizes gas loss. Immediately after filling, the cans pass into a seamer where a metal lid is dropped and double seamed with extreme force and precision, sealing in the carbonation. Cans are coated, checked, and shrink wrapped into trays, then palletized, just like bottles. Every mechanical step is governed by programmable logic controllers. These devices receive data from sensors monitoring flow rates, temperatures, torque values, fill levels, and carbonation pressure. If any parameter drifts beyond tolerance, the system adjusts in real time or stops the line. All systems communicate through a central SCADA interface, which displays status updates, alarm logs, and production metrics. Carbon dioxide is supplied from insulated bulk tanks located outside the plant. The gas enters the process through a vaporizer and filtration unit. Inline pressure regulators and flow restrictors ensure stable CO2 supply at all stages, from de-aeration to final carbonation. Clean-in-place systems activate between production cycles. A series of automated valves switch flow from product to detergent solution. Heated caustic cleans the tanks, pipes, carbonator, and filler valves. A rinse follows, and finally, a sanitizing solution is circulated. No disassembly is required. The process is monitored by conductivity meters and temperature sensors to verify cleaning effectiveness. Each segment of the Fanta production line is built for modularity and speed. Conveyor belts stretch across the plant in smooth arcs, synchronized by servo motors. Air conveyors are used in bottle transport to prevent mechanical contact. Accumulation zones between machines allow buffer space, so the line continues running even if one unit slows down. Production speeds for bottles can exceed 60,000 units per hour. Lines can operate at over 120,000 units per hour. The entire system is balanced to prevent bottlenecks. Fillers, labelers, and palletizers adjust their speed based on feedback from downstream equipment. Fill level is controlled to within 1.5 milliliters. Carbonation is regulated within a tolerance of 0.05 volumes of gas. Cap torque is checked to within 1 Newton meter. These tolerances are enforced by constant feedback and precision sensors. Label alignment is maintained through optical recognition. If the label wanders off-center by more than 2 millimeters, the labeler adjusts roller speed and cutter timing. Bundling film is tension controlled to avoid wrinkles or tears. Shrink tunnels have multi-zone heating, each controlled by thermocouples. Fanta's bright appearance comes from precise color dosing. The colorant solution is metered by mass flow controllers that inject it directly into the syrup blend. Any deviation in hue is detected by an inline spectrophotometer. For different flavors and regions, flavor concentrate tanks are changed out through quick connect valves. Each tank is barcoded, and the system will not run unless the correct flavor for the scheduled run is confirmed. All ingredient additions are logged, time-stamped, and tracked through the control network. Dr. Pepper begins with purified water. Municipal or well-sourced, the incoming supply is routed through a multi-stage treatment system. First, it flows through coarse filters that remove sediments and suspended particles. Then it enters activated carbon beds, which strip chlorine, off flavors, and organic traces from the water. Next, the liquid is pumped through a reverse osmosis membrane under high pressure. This removes dissolved minerals, bacteria, and microscopic contaminants. Final disinfection is completed using ultraviolet light and ozone. The result is neutral, sterile water, continuously recirculated through stainless steel holding tanks to maintain freshness and prevent stagnation. Inside the syrup room, Dr. Pepper's base formula is built in a precision blending tank. Liquid sugar, delivered in insulated tankers, is pumped into the tank through flow-regulated stainless lines. Into this stream, concentrated acids, natural and artificial flavors, colorants, and preservatives are dosed through servo-driven valves. These ingredients are not added all at once, but follow a timed sequence governed by a central control system. Stirring paddles agitate the mixture at programmable speeds. Viscosity sensors monitor the syrup's thickness. A pH probe verifies acid levels. An inline refractometer measures sugar concentration down to 1/10 of a Brix unit. As the mixture blends, the syrup's consistency is adjusted by adding chilled water or holding the solution under vacuum to prevent oxidation. Dr. Pepper's distinct flavor comes from a complex mix of flavor oils and acids, blended in sub-milliliter quantities by a dedicated dosing module with flow control down to microliters. Once all parameters are within specification, the syrup is held in a buffer tank under sealed conditions, continuously stirred and maintained at a stable temperature. Syrup is then piped into a proportioning unit where it meets the purified water in exact ratios. Typically, 1 part syrup is mixed with 5 parts water. Flow meters and precision control valves adjust the inputs in real time, ensuring consistency throughout the production run. This mixing takes place inside a turbulence chamber designed for immediate homogenization. The freshly blended beverage passes through a deaeration chamber. Here, the liquid is atomized under vacuum, breaking it into tiny droplets. This process removes dissolved oxygen that would otherwise cause off flavors or affect carbonation retention. Simultaneously, carbon dioxide gas is injected into the chamber to further displace any remaining oxygen. The temperature is dropped below 5 degrees Celsius to prepare the drink for carbonation. Carbonation takes place in a pressurized stainless tank fitted with high-efficiency gas diffusers. The beverage is injected with food-grade carbon dioxide at controlled flow rates. Pressure is held steady between 3 and 4 bar, while temperature is maintained just above freezing. Agitators inside the tank rotate slowly, ensuring uniform CO2 saturation without causing foaming or loss of gas. Carbonation level is verified with an inline CO2 analyzer, calibrated to within 0.05 volumes of gas. While the beverage is being carbonated, packaging operations are running in parallel. On the bottle line, polyethylene terephthalate preforms are fed into a rotary blow molder. Each preform is picked up by a gripper arm and passed through infrared heaters. When the plastic softens to the ideal temperature, it is transferred into a mold. High-pressure air inflates it rapidly, pressing it into the mold cavity and forming the final bottle shape. The molded bottle is immediately cooled and conveyed onward by air track systems that minimize surface contact. At the rinsing station, bottles are inverted and blasted with sterile water or filtered compressed air. After rinsing, the bottles are uprighted and fed into an isobaric rotary filler. This machine equalizes the internal pressure of the bottle with that of the carbonated beverage, minimizing gas loss during filling. Each bottle is clamped into a filling turret. A burst of CO2 is injected first to displace any residual air. Then the valve opens and liquid enters from the bottom. As the beverage level rises, gas is displaced upward and captured. Fill level sensors detect the target point, and the valve shuts instantly. The bottle rotates out and moves to the capping unit. Caps are sorted and oriented by centrifugal feeders. They are sterilized in line and delivered to the capping head, where servo-driven torque applicators screw them onto the bottleneck. Torque is measured in real time. Each closure is verified for tightness and alignment. If torque deviates from specification, the bottle is automatically rejected. After capping, the bottles move under an inkjet printer. Here, date codes, batch numbers, and production timestamps are applied to the shoulder or neck of the bottle. High-resolution cameras inspect the print for clarity and accuracy. Another vision system scans the bottle for correct fill level, cap integrity, and label presence. Labeling occurs at high speed. Rolls of pre-printed labels are fed into a rotary applicator. As each bottle rotates past, a servo-controlled arm presses the label onto the surface using adhesive or heat. Rollers smooth the label, edge to edge. A laser eye checks label alignment and triggers adjustments if needed. Labeled bottles are grouped at the bundling section. Depending on the product format, bottles are organized into groups of 6, 12, or 24. A clear shrink film wraps the cluster, and the bundle moves through a hot air tunnel. Controlled heating zones shrink the film tightly around the bottles without warping or melting. Next, the shrink-wrapped bundles are transported to the palletizing area. A robotic arm equipped with vacuum grippers picks up each bundle and stacks it onto a pallet following a programmed pattern. Slip sheets are inserted between layers to add friction and prevent collapse during transport. Once the pallet is complete, it is conveyed to a stretch wrapper. A rotating arm encircles it, applying plastic film from bottom to top. Film tension is automatically adjusted based on load profile and height. Parallel to the bottle line, the can line operates with higher throughput. Empty aluminum cans are depalletized and fed into a high-speed rinsing tower. After rinsing, cans enter a rotary filler similar to the one used for bottles, but designed specifically for metal packaging. The carbonated Dr. Pepper is injected under pressure. Immediately afterward, lids are placed on the cans and sealed with a double seamer. This forms an airtight seal between the lid and the can body. Cans are inverted, coated with inkjet printers, and inspected by a multi-camera system. Approved cans are organized into trays or shrink-wrapped into multi-packs. Robotic palletizers stack the finished units onto pallets. Final pallets are labeled, wrapped, and staged for shipping. Throughout the process, programmable logic controllers coordinate every movement. Each section of the line operates independently but communicates through the central control system. SCADA terminals show live readouts of temperature, pressure, line speed, fill volume, syrup ratio, carbonation level, and product counts. Alarms and trend logs are automatically stored for quality assurance. Carbon dioxide is supplied from an external cryogenic tank. The liquid gas is vaporized and filtered before entering the production system. Flow meters and pressure regulators maintain steady gas delivery to the de-aeration and carbonation units. Backup systems ensure uninterrupted flow. Clean-in-place systems operate at the end of each production run. Automated valves redirect flow through all product contact surfaces. Heated caustic detergent is pumped through tanks, pipes, fillers, and carbonators. A water rinse follows, and then a sanitizing solution is circulated. Conductivity and temperature sensors confirm cleaning efficiency. The entire cleaning sequence is logged and time-stamped. Dr. Pepper production lines are built for speed and adaptability. The blow molder can be adjusted for different bottle volumes. The labeler and filler can switch formats through software changes and tool-free part swaps. Servo motors drive most critical systems, allowing rapid changeovers with high accuracy. Filling accuracy is controlled to within 1.5 milliliters per container. Carbonation tolerance is held within 0.05 volumes of CO2. Cap torque is measured to within a fraction of a Newton meter. Label alignment deviation is limited to 2 millimeters. Every product is subjected to multiple points of verification before it leaves the line. Accumulators between machines allow for variable speed balancing. If a downstream unit slows, upstream conveyors store excess product temporarily. This prevents system shutdowns and maintains steady throughput. Conveyors are fitted with contactless sensors that monitor spacing and position, allowing real-time speed adjustment without collisions or jams. From raw water intake to final pallet wrapping, every phase of Dr. Pepper production is controlled, calibrated, and continuously monitored. No step is isolated. Syrup formulation, carbonation, filling, labeling, coating, packaging, and palletizing are integrated into a seamless flow of motion, temperature, pressure, and precision. The industrial process of bread production begins not with baking, but with an orchestrated balance of mechanics and chemistry where every gram of input is measured, every rotation of a blade is timed, and every degree of heat is calculated long before the first loaf begins to take shape. The cycle starts in the mixing room, where automated ingredient handling systems transport vast quantities of flour through pneumatic conveyors, drawing it from silos positioned outside the facility and funneling it in clouds of fine white powder into stainless steel batch hoppers that feed into the primary dough mixers. These mixers, towering and gear-driven, don't simply stir. They press, fold, and stretch the mixture with rotating arms that mimic the pressure and pull of hands, but at a scale and speed no human could replicate. At the moment liquid meets dry, the system kicks into life, and the rhythm of kneading begins. Inside the mixing chamber, every second counts. The speed starts slow to allow hydration, gradually increasing as gluten strands form and interlace, building the elastic structure that will define the shape, rise, and texture of the finished bread. Temperature sensors within the dough track the frictional heat produced during mixing, while torque sensors monitor resistance to ensure the dough reaches a consistent development profile. Cooling jackets around the mixer basin activate if necessary, keeping the dough within its ideal thermal range to avoid overproofing later in the process. Once the target consistency and elasticity are reached, soft, slightly tacky, extensible, but resilient, the dough exits the mixer through a bottom hatch, sliding as one heavy, cohesive mass into the next stage. A sheeter receives the dough next. Twin rollers compress it into a continuous slab, which then moves through a series of gauges to ensure thickness and density remain exact. This is not a shaping step, it's preparation. The flattened dough is directed into a high-capacity divider where a series of volumetric pistons cut the slab into uniform portions. These pistons measure by volume rather than weight, ensuring that even as humidity or temperature fluctuates slightly, each piece contains the exact same mass of air and dough combined. Once divided, the pieces are dropped into intermediate proofers, tall, climate-controlled chambers where the dough rests in a carefully maintained environment of warmth and humidity. It's here that the dough begins to ferment actively for the first time. The yeast, having been activated during mixing, releases carbon dioxide, expanding the structure from within. But this step isn't about final rise. It's about conditioning the dough, allowing it to relax after the physical stress of division so it can be molded without tearing. After a set number of minutes, each portion travels via conveyor to the molder. A set of guide rollers gently flattens the dough again. Then curling belts begin to shape it, rolling the mass inward to form a tight spiral that will become the loaf's interior structure. Pressure plates calibrate tension precisely, ensuring the outer skin of the dough wraps around the inner layers tightly enough to support rise, but not so tight that the loaf bursts during baking. Once molded, the loaves drop gently into metal baking pans, moving along a wide belt. Each pan is pre-lubricated with a fine mist of oil dispensed by a jet spray system to ensure clean release after baking. At this point, the pans pass through the final proofer, a long, enclosed tunnel where heat and humidity are kept within strict boundaries. Here, the loaves experience their final rise, swelling as fermentation accelerates. The gases trapped in the dough expand, the gluten matrix stretches to accommodate the volume, and the surface tension pulls tight, smoothing the top into a rounded dome. Sensors along the proofer track height, spacing, and proofing time. Any variation is logged, and the system will adjust conveyor speed or proofer climate to compensate. If the dough rises too quickly, the texture becomes irregular. Too slowly, and the crust may blister or fail to color evenly. Timing here is crucial. Baking must happen at the peak of fermentation activity to lock in that volume. Once the proofing cycle finishes, the pans emerge from the chamber and feed directly into the oven. The industrial oven is a continuous tunnel design, divided into multiple thermal zones with independent top and bottom heat controls. As the pans enter, steam injectors release a high-pressure burst across the loaf tops. This initial moisture keeps the crust soft in the early minutes, allowing for maximum oven spring as the bread expands rapidly under intense heat. The steam also sets the crust's structure and eventually contributes to its color and gloss. The baking process unfolds in stages. First comes expansion, where gases expand, alcohols evaporate, and enzymes break down residual sugars. Then comes gelatinization, as starches swell and set. Finally, Maillard reactions begin on the surface, turning the pale, supple dough into a rich, caramel-toned crust. The belt moves at a steady pace, calibrated so that by the time each loaf exits the last zone, it has reached the exact internal temperature required for complete bake, usually just over 96 degrees at the core. Exiting the oven, the loaves are hot and fragrant, but far too fragile for packaging. They roll forward on the conveyor and enter a spiral cooling system, a towering structure of coiled belts that winds upward, allowing the loaves to circulate through cooler air over the course of 30 to 40 minutes. Fans direct airflow from multiple angles, and vents above the line extract excess humidity to avoid condensation forming on the crust. As the temperature gradually drops, the crumb sets fully and moisture redistributes inside the loaf, ensuring softness remains throughout shelf life. Once cooled, the pans reach the depanning machine. A rotating arm, fitted with suction cups, lifts each loaf upward with precision timing, placing it onto a transfer belt while the empty pan continues onto a cleaning line. The pans are scrubbed with mechanical brushes, sprayed with sanitizer, and then dried by air knives before being stacked or returned to the molder for the next round. Meanwhile, the bare loaves now advance towards slicing and packaging. If the bread is destined for sale as whole loaves, it bypasses this stage, but most continue on to the slicer. This machine is built for speed. Multiple blades, mounted vertically in a row, oscillate at high speed as each loaf is pushed through by a belt-driven ram. The slices fall into alignment instantly, held together by guide rails as they move forward still in loaf shape. The next step is bagging. A plastic bag is blown open by a quick burst of air and guided into place by forming horns. The sliced loaf drops in, and a closing device, either a twist tie, tamper band, or plastic clip, seals the bag in one motion. An inline printer stamps each bag with a code indicating date, time, production line, and batch number. The sealed loaf is then guided onto a secondary conveyor for inspection. Cameras and weight sensors scan every packaged loaf. Any irregularities in size, shape, color, bag print, or closure are instantly flagged. Rejected loaves are diverted automatically, while the accepted product continues forward to be grouped for carton packing. Robotic arms pick up loaves in sets and stack them into shipping boxes, which are then sealed, labeled, and passed to the palletizer. The palletizing system uses multi-axis robotic arms to stack cartons onto wooden pallets in precise formations designed to prevent shifting or damage in transport. Slip sheets are placed between layers for stability. Once full, the pallet enters a stretch wrapper, where plastic film binds the load tight from base to top. A printed label is applied to the outer edge of the film, detailing product information, origin, destination, and tracking codes. Every action in this process is overseen by a centralized control network that connects mixers, dividers, molders, ovens, coolers, and packers into one coordinated line. Data flows constantly between stations. If the divider senses a shift in dough density, the molder adjusts tension. If the oven reports inconsistent browning, the slicer slows slightly to sync packaging output. Everything is in motion, yet everything is balanced. In a large-scale factory dedicated to the continuous assembly of sandwiches, every stage is a precisely engineered operation where timing, alignment, and consistency converge across hundreds of feet of synchronized machinery. And the process begins long before the first sandwich reaches the wrapper. It starts with bread loaves, already baked, cooled, and brought into the slicing system in racks, where they are automatically depanned, aligned, and fed into high-speed slicers fitted with ultra-sharp, serrated, or ultrasonic blades that oscillate thousands of times per second to deliver uniform, clean-edge slices without compressing the soft interior crumb or fracturing the crust. Once sliced, the bread slices travel by conveyor to a pre-alignment station, where camera-guided sensors and rotating guide arms ensure every slice is positioned in the exact orientation required for the next phase, which is the laying down of the base slices. These are distributed in pairs or rows, depending on whether the line is configured for single or multiple sandwich formats, and set evenly onto the moving belt with equal spacing between each set. The flow is constant, with no interruption between batches, and any variation in slice thickness or alignment is corrected in real time by pneumatic actuators and servo-driven guides that subtly adjust position and speed without halting the line. As the bottom slices approach the filling zones, the first application arrives in the form of spread, be it mayonnaise, mustard, aioli, butter, or any other emulsified or creamy base. A series of nozzles or roller spreaders applies a controlled layer, often using pulse pressure, to shoot a fan of spread across the surface, which is then evened out by a soft tipped roller or oscillating blade to ensure consistent coverage all the way to the edges of the bread. Sensors mounted above each lane scan the surface to confirm the presence, distribution, and thickness of the spread. And if coverage falls below specification, a feedback loop either reapplies the layer or removes the sandwich from the line. After the base layer is applied, the sandwich moves into the protein zone. Here, pre-sliced meats such as turkey, ham, beef, chicken, or plant-based alternatives arrive from upstream feed systems, where they have been portioned, weighed, and fanned into stacks by centrifugal feeders or vibratory shakers. These stacks are lifted by robotic pick-and-place arms equipped with vacuum suction or gripper fingers, depending on the product's texture, and laid gently onto each bread base with alignment controlled by high-speed imaging systems that adjust position in real time to match the orientation of the incoming slice. Every portion is weighed by inline check weighers before being applied, ensuring that each sandwich receives a uniform protein layer, with rejections happening instantly and automatically if tolerances are exceeded. Next comes the cheese layer, which moves from chilled stacks through a peeling and singulation system that separates individual slices, removes any protective film, and transfers them to a placement module. The cheese is picked and placed onto the meat with exact positioning, sometimes staggered depending on the sandwich style, and lightly pressed to ensure it conforms to the underlying surface without folding or hanging over the edge. The equipment adjusts for slice fragility using low-pressure vacuum heads and static control to prevent light cheeses from sticking to conveyors or deforming during placement. Vegetables come next, and this stage is often the most complex due to the variability in size, moisture, and fragility of the ingredients. Lettuce is dispensed from overhead hoppers with calibrated vibratory trays that gently shake shredded or leaf lettuce onto the sandwiches in measured volume, distributed evenly by spinning diffusers that sweep across the width of the belt. Tomatoes, cucumbers, and other sliced produce are fed from rotary magazines that release single slices in sequence, timed to the belt's movement, so each tomato lands directly at the center of the sandwich, guided by small airflow puffs or mechanical nudges if needed. Onion rings and other light layers are dispensed from spiral feeders or drop chutes, often with the assistance of static eliminators and light misting systems that prevent separation or clumping as the vegetables fall into place. If the top slice requires its own spread or condiment layer, a mirrored version of the first spreading station appears here, applying the layer just moments before the slice is joined to the assembled base. The top slice is picked by robotic arms from a secondary line of aligned bread slices, flipped if necessary depending on crust orientation, and gently pressed onto the assembled sandwich with just enough force to compress the stack into a unified structure without squeezing out fillings or deforming the shape. At this stage, the sandwich enters the compression and forming section. A series of soft rollers or belt presses applies uniform downward pressure to stabilize the build, enhance bite adhesion, and ensure the sandwich holds together through slicing, wrapping, and handling. The compression rollers are timed precisely to match belt speed, and the pressure profile is tuned to the product type, with more delicate sandwiches receiving lighter contact and denser builds compressed more firmly to lock the layers in place. Now fully assembled, the sandwich proceeds to the slicing station, where high-speed rotary or ultrasonic blades divide the product into the desired shape, typically halves or triangles. The slicing system is mounted on actuators that follow the motion of the sandwich as it moves along the belt, ensuring the blade enters and exits the loaf cleanly without tearing or pulling. Blade tension, sharpness, and angle are maintained through automated diagnostics, and the entire slicing module is flushed and sanitized between shifts to prevent cross-contamination. Cut sandwiches are now directed into the inspection lane, where overhead cameras and weight sensors verify slice alignment, edge definition, symmetry, and overall appearance. If a sandwich is misaligned, overfilled, underweight, or damaged during slicing, it is ejected by air blast or mechanical diverter before it reaches the wrapping system. The accepted sandwiches pass into the packaging zone, where the method of wrapping depends on the product's end use. For flow wrap sandwiches, the product enters a film feed tunnel where printed plastic film is drawn over and around the sandwich by guide belts, sealed along the back and ends by heated jaws that press and crimp the film closed in less than a second. A date coder prints production information onto the film surface just before the end seal. For chilled sandwiches sold in wedges or clamshells, the product is inserted by pick-and-place units into pre-formed rigid plastic containers. The lid is pressed or snapped into place and sealed with adhesive label strips or heat-sealed foil, depending on product design. Transparent sections are aligned with the sandwich face to ensure maximum visibility on shelf. Once wrapped, the sandwiches are grouped for boxing. A case packer counts the products and loads them into corrugated cartons, aligning each stack for minimal movement during shipping. Cartons are formed automatically from flat blanks fed into a forming station, sealed with hot melt glue or folded tabs, and labeled on the fly with barcodes, lot numbers, and shipping data. Each carton is scanned and weighed, and any deviation is flagged for inspection. The approved boxes move to the palletizing cell, where robotic arms stack them onto wooden or plastic pallets with layer patterns designed to balance weight and prevent shifting. The pallets are then rotated through a stretch wrapping station, where film is applied under tension from bottom to top, stabilizing the entire load for transport. A final label is printed and applied to the side of the pallet with a scanner-readable code containing the production batch, shift, line number, and timestamp. Bagel production at factory scale is a continuous ballet of movement and transformation, where the dense, chewy character of each finished product is the result of precisely sequenced operations carried out by synchronized machines, each tuned to interact with dough in a way that preserves its integrity, develops its structure, and creates the exact conditions required for that unmistakable crust and crumb. It all begins in the dough room, where flour moves from towering silos into enclosed conveyor tubes, descending by weight into a batcher that draws measured volumes of water, salt solution, yeast suspension, and additional agents through chilled, jacketed feed lines that maintain temperature consistency from the first pump to the final discharge into the mixer. As the ingredients come together in a high-capacity spiral mixer, the arms begin turning slowly, cutting through the thickening mass with powerful, spiraling force, pulling the flour into the water and folding the developing dough inward from all angles. Unlike lighter breads, bagel dough requires far more resistance and strength, so the machines are set to operate under heavier torque, and the texture is intentionally firmer from the start. Temperature probes track internal friction heat. If the dough rises beyond the target, a cooling system kicks in, circulating chilled water through the ball's outer jacket, allowing the dough to strengthen and ferment without overheating. The mixing continues until the dough becomes tight, elastic, and resilient to touch, ready not for shaping, but for division. At this point, the dense dough is released through a bottom hatch and fed directly into a portioning unit that slices it into thick, consistent strips, each one calibrated for weight and volume by servo-guided sensors that track the length, width, and compression of the dough strand as it moves forward on the belt. These portions are then carried forward to the bagel former, a specialized system unique to this category of baked goods. Here, each dough piece is rolled into a rope between two textured conveyor belts, gradually tapering the ends for seamless closure. The ropes are then transferred to the forming drum, a rotating cylinder fitted with a center plunger and an outer ring guide that picks up the rope, curls it into a circle, and presses the ends together into a seamless loop without pinching, tearing, or folding. Formed bagels are deposited onto a wide, dusted conveyor belt, each one spaced perfectly from the next by indexing arms that keep rows uniform as they head toward the proofing section. At this stage, the dough is still dense and compact and needs controlled time to relax and ferment before any further processing. The trays of raw bagels enter an enclosed, temperature and humidity regulated proofer where warm, moist air surrounds the dough, gently encouraging expansion without aggressive rise. Over the next 15 to 20 minutes, the yeast becomes active, releasing carbon dioxide and creating a subtle softness beneath the taut exterior. Proofing times are controlled to the minute, with sensors tracking volume gain and relative humidity in every lane of the chamber, so that every bagel arrives at the next step with the same bounce, shape, and tension. What follows is the defining characteristic of bagel production: boiling, or more accurately, a high-temperature water bath that sets the outer crust before baking begins. As the proofed bagels exit the chamber, they move onto a boiling belt that carries them through a long stainless steel trough filled with circulating water, often mixed with barley malt or a similar solution to enhance browning later in the oven. The bagels float as they enter, and a set of rotating paddles gently submerge each one to ensure even exposure. They spend only seconds in this bath, but it's enough to gelatinize the starches on the surface, locking in shape and creating the foundation for that dense, glossy crust. Once boiled, the bagels are lifted from the water by an upward sloping mesh belt and allowed to drain momentarily before entering the topping section, where optional finishes, sesame, poppy, onion, salt, are applied. This happens through a combination of timing, moisture, and gravity. The wet surface of each bagel acts as a natural adhesive, so as they pass under overhead hoppers or through rotary topping applicators, the seeds or seasonings fall onto the dough and stick cleanly to the surface. Excess toppings are collected by a vibrating reclaim system beneath the belt, filtered and returned to the hopper for reuse, ensuring nothing is wasted and every bagel receives an even coating. The topping section leads directly into the oven, a massive tunnel-style system divided into multiple thermal zones that gradually bring the bagels from boiled to baked over the course of 10 to 12 minutes. The first zone introduces radiant heat to activate oven spring, but because the crust is already partially set, expansion is modest and the shape remains tight and uniform. In the middle zone, the crust begins to brown, driven by Maillard reactions that create the deep caramel tones and toasty aroma typical of well-baked bagels. The final zone balances color and internal moisture, holding a slightly lower heat to allow the core temperature to rise without burning the toppings. Throughout the bake, airflow is precisely directed and humidity is adjusted by steam injection valves to control crust thickness and finish. As they exit the oven, the bagels are fully formed, firm to the touch, richly colored, with a light sheen from the boiling stage and a tightly structured crumb inside. But at this point, they're still over 90 degrees Celsius internally and too hot for packaging, so the belt carries them into a spiral, cooling tower, a towering column of coiled belt that winds upward, allowing each bagel to travel along a rising path while being cooled by ambient air and filtered ventilation. Over the next 20 to 30 minutes, the internal temperature drops steadily and the crust stabilizes, preventing condensation and preserving the chewy exterior texture. From the base of the spiral, bagels are sorted by product type: plain, topped, seeded, and diverted into corresponding packaging lanes. If they are to be sold whole, they continue uncut, passing through alignment rails and into flow wrapping tunnels, where printed film encloses them in a tight, sealed wrap that's closed by heat-sealed seams on the underside. For multi-packs, bagels are counted and stacked automatically, transferred into trays or bags using pneumatic plungers or robotic suction heads, and sealed with clips, twist ties, or tamper-proof labels. Batch codes, production times, and expiration dates are printed by inline thermal inkjet systems on the package surface. If the bagels are destined for pre-sliced use, they proceed to the slicing unit, where a high-speed circular blade, often with ultrasonic vibration, cuts horizontally through each bagel's midpoint, while the product is held firmly in a compression cradle that prevents movement or tear out. The two halves remain paired and are then rewrapped as a sliced unit, ready for sandwich use or toasting. The sliced bagels are also inspected by weight, diameter, and color, with overhead cameras tracking any deviation in cut depth or alignment and removing out-of-spec product instantly from the conveyor. From there, the finished and packaged bagels are transferred into carton loading stations. A mechanical arm stacks them into pre-formed boxes, which are then sealed, labeled, and conveyed to the palletizing zone. Here, a robotic palletizer organizes the cartons in tight formations, applying slip sheets between layers and wrapping each pallet in film to protect it during transport. Each pallet is labeled with a scannable tracking code that contains all relevant production data: time, line, operator, batch, and destination. Throughout this entire process, every machine, every transfer, and every transformation is governed by a central control system that monitors line speed, batch integrity, ingredient flow, humidity, oven temperature, belt timing, and packaging rates. Adjustments happen automatically. If the boiling water cools by 2 degrees, the belt speed slows. If the oven heat drifts too high in zone 3, airflow is redirected. If the topping adhesion falls below threshold, an alert is triggered, and the hopper motor pulses slightly to shake more seed onto the line. Nothing here is guesswork. Everything is calculated. Bagels don't just bake. They're shaped, built, boiled, and finished by systems that never stop watching, adjusting, and maintaining perfect rhythm. The machines don't work alone, but in coordinated layers, each one tuned to preserve the dense structure, glossy crust, and unmistakable bite that defines a factory-made bagel. In just over an hour, a lump of flour and water is transformed into something firm, chewy, finished, and sealed, ready to ship, ready to slice, ready to toast, and repeated thousands of times per hour without pause. Chef Boyardee beef ravioli begins its industrial journey with the delivery and preparation of raw ingredients in a tightly controlled, high-capacity food processing environment designed for continuous, large-scale output. At the very start, durum wheat semolina arrives in bulk and is stored in tall silos connected by enclosed pneumatic systems that transport measured amounts of flour into industrial mixing vats. These mixers operate under vacuum to prevent air entrapment in the dough, which could compromise the texture of the final pasta. Water is injected through a flow-regulated system, and the dough is mixed into a dense, elastic mass that is then conveyed into a dough sheeter. Inside this machine, large stainless steel rollers gradually press the dough into a long, uniform sheet of precise thickness. Sensors constantly monitor and adjust roller pressure, sheet thickness, and alignment in real time, ensuring consistent dimensional control across thousands of linear feet of pasta every hour. As the pasta sheet continues on its route, it approaches the forming station. Here, the sheet is split into top and bottom layers using a synchronized cutting system, and the beef filling, prepared simultaneously on a parallel line, is introduced between them. The beef mixture is produced in massive steam-jacketed kettles, where ground beef is cooked with tomato paste, spices, salt, and stabilizers. High-shear mixing blades ensure uniform blending, while thermal sensors regulate the internal temperature to avoid overcooking. Once cooked, the beef filling is transferred to positive displacement pumps that feed the filling directly into the ravioli former. Precise nozzles inject a consistent amount of filling at evenly spaced intervals onto the bottom sheet. The top sheet is laid over it, and the two layers are pressed together by a rotary die that seals and cuts the individual ravioli pockets in one continuous motion. Any excess dough around the edges is collected and recycled back into the dough feeder. The freshly formed ravioli travel along a mesh belt through a par cooking tunnel, where a curtain of low-pressure steam partially cooks the pasta just enough to firm the structure and set the seal. The par cooking chamber is followed by a high-efficiency air chiller that quickly cools the product to prevent further cooking. From here, the ravioli move to the accumulation table that feeds the canning line. The tomato sauce, which is made in a separate set of kettles, is already being prepared in parallel. This sauce includes tomato puree, vegetable oil, spices, and sugar, blended in high-capacity vats, equipped with wall-scraping agitators to ensure uniform cooking and prevent scorching. The sauce is filtered to remove any large solids, skins, or seeds, and is kept hot in jacketed holding tanks while waiting to be dispensed. The canning line is a seamless, high-speed process that brings ravioli and sauce together inside sterilized metal cans. Empty cans are first fed from depalletizers into an inverted position for steam or air sterilization before being returned upright and carried along a conveyor. A timed filling system first drops a preset quantity of ravioli into each can. Next, a separate nozzle dispenses a specific volume of hot tomato sauce into the same can. Load cells and vision sensors measure weight and volume in real time, instantly rejecting any can that falls outside tolerance. To maintain long shelf life, the filled cans receive a quick injection of steam into the headspace to displace oxygen, which is critical for preventing spoilage and discoloration. The cans then proceed to the seaming machine, which applies and crimps the metal lids at high speed using rotary chucks that spin and press the lids into place with a hermetic seal. Once sealed, the cans are routed into a massive rotary retort, a large pressure chamber where the canned ravioli undergo commercial sterilization. This thermal processing step is one of the most critical phases in the entire operation. Inside the retort, the cans are exposed to pressurized steam at temperatures above 121 degrees Celsius for a fixed period, calculated according to product density, can size, and altitude. The process is tightly controlled by a programmable logic controller that adjusts heat input, steam pressure, and timing with precision, ensuring that the interior of each can reach the temperature needed to destroy any potential microbial contaminants. This sterilization method allows the product to be shelf-stable for over a year without the use of chemical preservatives. As the cans exit the retort, they are rapidly cooled using a countercurrent water system that brings the internal temperature down quickly while avoiding thermal shock that could warp the can. After cooling, the cans are dried using air knives that blow off any surface moisture. They then move into the labeling area, where each one is printed with a unique production code, expiration date, and batch number using high-speed inkjet printers. These codes are logged in a centralized database that allows full traceability of every can, linking it back to the exact batch of dough, filling, sauce, and sterilization cycle. This traceability system is essential for maintaining quality control and complying with food safety regulations. Labels are applied using rotary labelers, which align the cans, dispense the adhesive-backed labels, and press them smoothly onto the curved surfaces. Any can with a misapplied or missing label is automatically diverted off the line. The labeled cans proceed to the packing station, where they are grouped into shrink-wrapped multi-packs or loaded into cardboard trays, depending on distribution requirements. Robotic arms equipped with vacuum suction heads stack these cases onto pallets in a tightly packed, interlocked pattern that ensures transport stability. Each pallet is weighed, stretch-wrapped, and labeled with a scannable barcode that encodes the full logistics data for shipping and warehouse integration. Completed pallets are conveyed into a climate-controlled warehouse area, where ambient temperature is maintained within a narrow range to preserve product integrity and packaging quality. The inventory system automatically logs each pallet into a virtual grid based on product type, batch, and destination. Orders from distribution centers are matched against inventory using software that assigns retrieval instructions to automated guided vehicles. These vehicles transport the pallets to loading bays where they are prepared for shipment on temperature-managed trucks. Throughout this entire process, every step is monitored by industrial control systems that log thousands of data points per minute, from moisture content in dough to the pressure in the retort chamber. If any sensor detects an anomaly, whether it's a filling inconsistency, temperature deviation, or mechanical irregularity, alarms are triggered, and corrective protocols are initiated automatically. Quality assurance technicians also perform random sampling at every stage, testing dough elasticity, filling viscosity, sauce pH, seam width, and internal vacuum levels. Any sample that fails a parameter prompts an investigation and potential quarantine of the related batch. The design of this factory setup allows for continuous production for 24 hours a day, with modular maintenance schedules that let individual lines shut down without halting the entire operation. Cleaning in place systems run through every tank, pipe, and pump at regular intervals, using cycles of hot, caustic solution, followed by acid rinses and pure water flushes. This level of automated sanitation prevents bacterial buildup and maintains a sterile environment, especially critical in the post-cook zones. By the time a single can of Chef Boyardee beef ravioli reaches the supermarket shelf, it has passed through dozens of machines and control checks, undergone multiple thermal transformations, and been assembled from raw materials that were processed, cooked, combined, sealed, and sterilized within minutes of each other. The result is a uniform, shelf-stable product that replicates the exact same taste, texture, and aroma across millions of cans each year, a feat of engineering, timing, and integrated automation performed at industrial scale. The industrial production of gnocchi begins with a continuous intake of raw potatoes selected specifically for their starch content, moisture levels, and uniformity. These potatoes arrive in bulk, often delivered in heavy-duty totes or truckloads, and are immediately transferred into stainless steel receiving bins. From here, a water flume system propels the potatoes toward the washing stage using a circulating stream of filtered water, which not only moves the product gently, but also performs a preliminary rinse that separates dirt, rocks, and field debris. The potatoes pass into a rotary drum washer, a large cylindrical cage lined with soft baffles and rotating paddles. Inside, multiple high-pressure spray jets clean the surface of every tuber, while slow drum rotation ensures even exposure. Wastewater is filtered and recycled back into the flume, maintaining efficiency while minimizing fresh water consumption. Once cleaned, the potatoes move onto inclined conveyor belts and pass beneath an optical sorter that detects misshapen or heavily blemished specimens. Air jets eject any defective potatoes instantly. The remaining load proceeds toward the steam peeling chamber, a sealed environment into which high-pressure steam is injected rapidly. This process loosens the skins in seconds without penetrating deeply into the flesh. A sudden pressure drop follows, causing the skins to rupture. As the chamber releases its load, rubber fingers or gentle high-pressure sprayers remove the loosened skin without damaging the underlying structure. The peeled potatoes then travel along a belt for final inspection before cooking. Next, they enter a cooking tunnel equipped with rotary steam ovens or belt-fed boiling sections. These systems are calibrated to cook each potato evenly, using internal probes to track core temperature without overcooking the starch. The cooking time is precisely tuned so the flesh softens just enough for mashing while preserving structural integrity. Cooked potatoes are discharged directly into screw-fed conveyors that deliver them into industrial mashing systems. These mashers force the hot potatoes through perforated plates using rotating paddles, breaking them into a uniform, lump-free mash with consistent density. This mash is transferred into stainless steel hoppers, fitted with agitators to prevent settling while it awaits mixing. Simultaneously, dry ingredients are prepared using a separate set of feeders. Wheat flour, salt, and any dry seasonings are metered in precise ratios using volumetric or gravimetric dispensers, ensuring repeatable consistency across large batches. These dry components meet the hot mash in horizontal ribbon mixers or twin screw extruders, where the dough is developed. If eggs or other binders are used, these are injected through nozzles timed to match the flow rate of the dry and wet components. Dough temperature, torque, and consistency are continuously monitored, allowing automated systems to adjust mixing speed or ingredient dosing in real time. As the dough reaches its final form, it exits into forming lines. These lines are fitted with multi-head extrusion units that shape the dough into cylindrical ropes, which are automatically guided into a cutting module. Guillotine blades or rotary knives slice the ropes into uniform pillow shapes at high speed. Each piece is then transferred onto a vibrating sorting table to prevent clumping and ensure even spacing before shaping. For traditional gnocchi, a patterned drum or stamp roller presses the surface of each dumpling, forming the signature ridges. These ridges aren't just for appearance. They help hold sauces and ensure the texture is consistent during cooking. The raw gnocchi are now ready for par cooking. Depending on the product type, they may enter a steam tunnel, boiling water bath, or continuous blanching system. For fresh gnocchi, a short steam treatment helps gelatinize the starch on the outer layer, setting the shape without fully cooking the interior. In the case of shelf-stable or refrigerated products, boiling is used for more complete cooking. The gnocchi travel through the system on mesh conveyors that allow water to drain or steam to vent. Those that float prematurely, often indicating trapped air or structural failure, are skimmed off and diverted. Finished gnocchi are cooled rapidly with air or chilled water sprays to stop the cooking process immediately. Cooling is followed by drying. Par-cooked gnocchi are passed through air tunnels or oscillating belts with forced, filtered airflow. This surface drying stage ensures the pieces don't stick together in packaging. In some configurations, a fine coating of semolina or rice flour is applied to further reduce surface tackiness. At this stage, the gnocchi are fully formed, partially cooked, and ready for packaging or freezing, depending on the final product category. Fresh gnocchi are directed into multi-head weighing systems that portion exact quantities into pre-formed pouches. These machines calculate the best weight combination from multiple hoppers to ensure precision. Pouches enter a modified atmosphere packaging (MAP) chamber, where the ambient air is replaced with a mix of inert gases like nitrogen and carbon dioxide. This extends shelf life by inhibiting microbial growth and oxidative reactions. Sealing jaws then close each pouch under pressure, forming airtight seals. Pouches exit the MAP system and are immediately inkjet printed with production codes, expiration dates, and batch tracking information. For frozen gnocchi, the cooled pieces bypass MAP and instead travel to the freezing tunnel. This is a long conveyor system housed within an insulated chamber where fans blow extremely cold air across the product. The process is known as IQF, or individual quick freezing, which ensures that each gnocco freezes separately, avoiding clumps. Once frozen solid, the gnocchi are packaged in bulk or consumer-ready bags, sealed, labeled, and sent to deep freeze storage. Regardless of the format, every package goes through a metal detection and X-ray inspection station before final packing. These machines identify any potential contamination from production, like stray metal fragments from worn machine parts, and immediately reject any affected units. Packages that pass inspection proceed to robotic case packers, where arms equipped with vacuum grippers load them into cardboard boxes. The boxes are sealed, barcoded, and sent to automated palletizers that stack them according to optimized loading patterns. Each pallet is stretch wrapped and labeled with a traceable QR code or barcode, then entered into the warehouse management system. The final stage is cold storage and distribution. Refrigerated products are stored at 2 to 5 degrees Celsius, while frozen products are kept at 18 or colder. High-density shelving is managed by ASRS units, automated storage and retrieval systems that navigate the warehouse floor with programmed efficiency. When an order is placed, the system retrieves the correct pallet, stages it at the loading dock, and synchronizes it with outbound transport logistics. Goods are typically moved in temperature-controlled trucks that maintain strict thermal stability to prevent texture loss or microbial growth during transit. Quality assurance labs operate in parallel with the production floor. Technicians pull random samples from each batch to assess moisture content, cooking time, bite texture, and microbiological safety. These samples are cooked and evaluated for structure, flavor retention, and resistance to disintegration. Texture analyzers apply calibrated pressure to measure chew resistance, while high-resolution cameras measure shape retention after boiling. If a batch fails any parameter, the corresponding lot is flagged in the system and held for further review or disposal. Cleaning and maintenance operations take place in modular shifts. All lines are fitted with cleaning in place (CIP) circuits, automated wash systems that flush tanks, hoses, pumps, and valves with caustic solutions, hot water, and acid rinses. This ensures hygienic conditions even when production is running continuously. Key areas like mashing stations, flour feeders, and packing heads receive manual cleaning daily, and critical equipment like extrusion heads are dismantled, brushed, sanitized, and reassembled before every major production run. Throughout the process, every detail is monitored by supervisory control and data acquisition (SCADA) systems. These systems provide operators with real-time dashboards showing dough temperature, flow rates, extrusion torque, cutter speed, par cooking dwell times, and fill weights. Alerts and automated corrections ensure that even minute deviations are caught and resolved without interrupting production. Historical data is stored and reviewed to improve yield, reduce waste, and maintain traceability. From field harvested potato to the final sealed pouch or frozen bag, gnocchi production at factory scale is a precisely tuned sequence of heat, pressure, shaping, and preservation, all balanced to protect the soft, pillowy character that defines this classic product. What begins as humble starch and flour becomes thousands of identical dumplings per hour, delivered with perfect form, flavor, and shelf stability. Lasagna production in a factory is a multi-phase, highly integrated process that combines pasta sheet manufacturing, meat sauce preparation, cheese blending, layer assembly, baking or pasteurization, portioning, packaging, and cold chain logistics, all synchronized to ensure consistency, safety, and scale. Unlike dry pasta or single-element products, lasagna is a fully prepared, multi-ingredient dish. This makes its industrial production uniquely complex, requiring extensive machinery and tightly controlled automation to ensure that every slice mirrors the expected texture, flavor, and structure. The process begins with pasta sheet production. Durum semolina flour is delivered in bulk and stored in silos. From there, it moves through pneumatic conveyors into high-capacity mixing vats where it's combined with water under vacuum. This vacuum mixing reduces air bubbles and improves dough elasticity. The dough is then extruded into wide sheets using continuous sheeting rollers. These rollers compress and stretch the dough between pairs of calibrated rollers, gradually flattening it to a specific thickness, typically less than 1 millimeter. Optical thickness sensors positioned along the rollers feed data into a closed-loop control system that makes micro-adjustments in real time. The continuous pasta sheet is then guided onto a conveyor that passes through a high-temperature dryer tunnel. This dryer uses forced hot air to reduce surface moisture and firm the sheet slightly without fully cooking it, which gives it the pliability needed for layering. After drying, the sheet moves into a cutting system. Depending on the product specifications, a rotary knife assembly cuts the sheet into wide rectangular panels, each aligned with the intended tray dimensions. A rejection arm automatically discards any sheets that are torn, folded, or non-uniform. While pasta sheets are being prepared, the factory simultaneously produces the meat sauce. Ground beef is loaded into steam-jacketed kettles equipped with high-speed agitators. The meat is seared first, breaking it into small crumbles. Tomato puree, tomato paste, oil, chopped onions, garlic, herbs, and seasoning are metered into the kettles through automated valves. The sauce is simmered while being agitated to prevent scorching and ensure uniformity. During this time, inline temperature probes and brick sensors monitor thickness, sugar levels, and viscosity. Once the sauce reaches its target consistency, it's pumped through heated stainless steel pipelines into holding tanks that maintain it at a constant temperature until assembly. In a separate mixing area, the cheese component is prepared. Depending on the recipe, this may include a blend of ricotta, mozzarella, and parmesan. Ricotta is delivered in cooled totes and mixed with stabilizers, herbs, and sometimes eggs in vertical mixers to ensure even distribution. Shredded mozzarella and grated parmesan are stored in silo-like hoppers connected to vibratory feeders that portion out cheese by weight for each layer. Now begins the core of the lasagna production, layer assembly. This takes place on a continuous assembly line with moving trays or belt-mounted mold forms. Each tray or mold is sanitized prior to filling and travels under a set of ingredient dispensers. First, a measured amount of meat sauce is deposited into the bottom of the tray by a servo-controlled nozzle that moves in a sweeping pattern to ensure full coverage. A vacuum depanner then places a single pasta sheet on top, aligning it precisely over the sauce. This is followed by a ricotta deposit nozzle that pipes a uniform, ridged bead of cheese across the sheet, which is then smoothed by a vibrating spreader bar. Another pasta sheet is placed, and the cycle repeats: sauce, pasta, cheese, until the required number of layers is achieved. The top layer typically ends with sauce and a sprinkling of shredded mozzarella and parmesan dispensed by oscillating auger heads that shake cheese evenly over the tray surface. Before baking or pasteurization, Some lines include a brief compression station where a flat paddle gently presses down on the lasagna to remove air pockets and improve bonding between layers. The fully assembled trays then move on to the thermal treatment phase. If the lasagna is intended to be frozen, the thermal step may be pasteurization, which involves heating the product just enough to kill bacteria but not fully cook it. For chilled or ready-to-eat versions, full baking is performed. Trays enter a convection oven that circulates heated air at over 180 degrees Celsius. The line speed, tray height, and internal oven temperature are all controlled to ensure even cooking from edge to center. Internal temperature probes inserted in sample trays verify that core temperature targets are achieved and held for a specific time to guarantee food safety. Once cooked or pasteurized, the lasagna must be cooled rapidly to prevent microbial growth and lock in texture. This is done through a tunnel chiller, where trays pass through zones of progressively colder air, sometimes supplemented by glycol-cooled plates that pull heat from the tray bottoms. The cooling process must reduce the product from over 80 degrees Celsius to below 5 degrees Celsius within a few hours, which is regulated by airflow, dwell time, and temperature differential. Sensors at the tunnel exit confirm that each tray meets cooling requirements. Once cooled, the lasagna is portioned and packaged. If individual servings are required, the tray is sliced by ultrasonic knives that vibrate at high frequency, cutting cleanly through dense layers without dragging or distortion. For family-size portions, the entire tray may be sealed as is. Packaging formats include vacuum-sealed trays, film-sealed thermoformed, packages, or sealed and labeled foil trays, depending on the target market. Modified atmosphere packaging may also be used for chilled products to extend shelf life. Oxygen levels are flushed and replaced with inert gases before the final seal is applied. Each sealed package passes through a metal detector and X-ray unit to ensure it contains no foreign materials. It then receives an inkjet printed label showing the batch number, production date, expiration date, and a scannable code for traceability. The labels are verified by vision systems to confirm placement, readability, and correctness. Any mislabeled unit is automatically rejected into a separate channel. From there, packages are grouped into boxes using robotic case packers. These cases are palletized by automated arms that stack them in stable formations, alternating layers for weight distribution. Stretch wrapping units seal the full pallet, and each is tagged with a warehouse tracking code before being moved to cold storage. Depending on the product type, it may be stored in refrigerated or frozen conditions. Pallets are managed by automated guided vehicles that transport them to pre-assigned racks in high-density storage systems, where inventory software tracks position, age, and destination. Throughout this process, the factory uses a SCADA, supervisory control, and data acquisition system to monitor every critical variable. Dough hydration levels, pasta sheet thickness, sauce viscosity, cooking times, and packaging seal integrity are all tracked in real time. Historical data is stored and analyzed to identify patterns, correct deviations, and optimize throughput. If any parameter falls outside the designated range, alarms are triggered, and the system automatically isolates affected batches for inspection. Cleaning and sanitization cycles are embedded throughout the plant. Clean-in-place systems run through the pasta extruders, sauce kettles, and piping lines at scheduled intervals. Belts, mixers, and conveyors are cleaned using automated foamers and high-pressure rinsers between production runs, often overnight. This ensures the plant can shift from producing meat lasagna to vegetarian or gluten-free variants without cross-contamination. Every few hours, quality assurance teams perform manual inspections of randomly selected trays, assessing factors such as layer adhesion, ingredient distribution, flavor profile, pH level, and slice integrity. Cooking tests are conducted to see how the product behaves in a domestic oven or microwave, ensuring the consumer experience matches factory standards. The entire process, from flour and raw meat to finished boxed lasagna, is designed for speed, consistency, and hygiene. Trays of lasagna move continuously through a loop of automation, blending traditional culinary elements with industrial engineering. The meat must be savory but not greasy. The pasta should remain tender after reheating without breaking apart. The cheese should melt and set without seeping or becoming rubbery. Each of these qualities is maintained not through guesswork but through precise mechanical control over every movement, temperature change, and ingredient ratio.